Kale, kale, allez, kale,
Ouais, nazoka yo.
kale,
Ouais, nazoka malamu. Eza bien.
YouTube, kale. Quand il joue, YouTube,
Ouais, nazoka.
YouTube,
Ouais, nazoka malamu. Eza bien. Oh, of course.
So good morning, everyone, and welcome to the second day of the Focus Meeting 7 on the new horizons at the interface between computational astrophysics and big data. We would be having 5 talks today, out of which one is online. And the first talk is essentially an invited talk by Xingyu Chen from University of Texas at Austin. And she would be presenting on the science opportunities and challenges with next generation ground-based gravitational wave observation. Xingyu, the floor is yours.
Thank you. Good morning, everyone. Hi, I'm Xingyu. Today I'm going to present in a topic that's actually very different from other topics in this session. Given the diversity of the participants in this session, the plan for this talk is I'm going to give a quick overview of, for ground-based gravitational wave observations, what kind of exciting science we are trying to do. And then I'm going to identify several big challenges we face in our field. Okay, so let's get started with the sources for gravitational waves. Throughout my talk, I'm going to use the orange ball to represent a neutron star and the blue one for a black hole. And these two types of stars, they compose of all the gravitational wave events we have detected so far. Let's say you have 2 black holes, they rotate around each other in binary. Then they would emit energy in the form of gravitational waves. During this phase, we call it the in-spiral phase, the amplitude and the frequency of the gravitational wave signals would stay almost the same. So the gravitational waveform will look more or less like a sinusoidal wave, as you see on the left-hand side. You will have to wait until almost the end of this evolution with the orbit of the binary shrink and the amplitude and the frequency of the signal shoots up. In the end, these 2 black holes, they merge into one big one. It might take a small amount of time for the system to stabilize itself. That's what we call the ring-down phase. So in spiral, merger and ring-down, these are the 3 major components for all the gravitational wave signals come from the compact binary mergers. More detailed like physical properties of this binary, they are gonna change the waveform by a bit in more details, and we'll come back to this later. And these are our detectors. As you heard yesterday from the plenary talk, we are currently in our 4th observing run. And right now we have the LIGO Livingston site and Virgo operating. LIGO Hanford is going through some temporary shutdown to diagonalize for the noise and do some repairing. And hopefully by the end of our current observing run, the Kagra, the Japanese detector, could join us as well. And we do have plan to upgrade the sensitivity of our current detector all the way to almost a mid or to late 2030s, which we're gonna try to push the sensitivity limits with our current facility, so the maximum we can do. And hopefully by then, the LIGO India could join us as well. In parallel, the community is also pushing the plan for next generation ground-based gravitational wave detectors, including the US-led effort, the Cosmic Explorer, and Einstein Telescope, that is a European version. And the goal for these next generation detectors is to essentially detect all the stellar mass compact binary mergers in the universe. Okay? But even with our current generation of detectors, we have already detected hundreds of binary black holes mergers. We have confirmed more than 90 binary black holes mergers in our first 3 observing runs. And with our current observing run, we have another about 120 more candidates. These binary black holes merger, they have mass span around a very wide range of mass range. That's what you see on the vertical axis there. We also have detected smaller systems. So merger between two neutron stars, especially the very famous event, GW170817, it not only comes with gravitational wave signal, but also electromagnetic counterpart, including short gamma ray burst and kilonova emissions, as you heard yesterday. And these kind of combination of information from EMM observations and gravitational observations is gonna bring a lot of great science, this multi-messenger science. And we'll come back to this later too. We have also detected a third type of system, the merger between a black hole and a neutron star. And you already heard about it in plenary yesterday as well. We have several detections of these neutron star black holes merger. So with all these exciting detections, there's so much science we can do, ranging from fundamental physics, cosmology, nuclear physics to astrophysics. Starting with astrophysics, one big question we are trying to answer is the binary formation history. How did this binary found each other in the past? What happened in their evolutions that in the end lead to the merger? That is one big question we are trying to answer with all these detections. We'll also come back to this later. We can also use these detections to test many fundamental physics theories. For example, that short gamma ray burst that comes with the binary neutron star merger, GW170817, it arrived only 1.7 seconds after the arrival of the gravitational wave signal, which indicates the speed of the gravitational waves are so close to the speed of light. And we have also conducted various other different types of tests, including tests against general relativity, and so far Einstein has been doing fine. We want to do cosmology as well. Actually, this is my core science. Gravitational wave signal from their amplitude, we can directly determine the distance, how far away those compact binary mergers are to the Earth. So with this distance measurement, and if we somehow determine the redshift of this system as well, for example, from the observation of electromagnetic counterpart, then we can constrain the cosmic expansion rate. Especially, we are interested in the local universe expansion rate. That's what's so-called the Hubble constant, H0. Because of this big tensions, I believe, possibly all of you have already heard of, the tension of the H0 measurement between the cosmic microwave background observations and some of the local measurement. Gravitational wave observation as an independent tool, they can possibly shed light on these big tensions. Moving on to nuclear physics. One big difference between the gravitational signals emitted from binary black holes mergers and neutron star mergers, that's what you see in the bottom, is that these neutron stars, when they get so close to each other, these neutron stars, they can be tidally deformed by their companion stars. And this tidal deformation would change the gravitational waveform they emit. So from the gravitational wave signal, we can observe tides. And how do these tidal signals look like in the gravitational waveform would depend on the properties of the nuclear matters inside the neutron stars, which is something actually very difficult to measure on Earth with experiments or to predict them theoretically. Neutron stars turns out to be an ideal lab for us to test the property, the physical property of these extreme matter. These matter are under very high density, low temperature. And that is something we have done with the observation of GW170817 as well. Finally, we are here in South Africa, where they used to produce a lot of gold. And actually, I just checked this morning, they still lead the production of platinum in the world at the moment, like right now. So where did this gold, platinum, and a lot of heavy elements were produced in the universe? That is another big mystery. Neutron star mergers could create a neutron-rich environment after the system merge. And that neutron-rich environment could allow for the rapid neutron capture nuclear synthesis to happen, the so-called R-process nuclear synthesis, which is a critical process for the protection for many of these heavy elements. So from the observation of neutron star mergers, we can try to study this problem. Okay, so how do we do all these cool science? Well, it certainly relies on the collaboration with many different fields. We will need great instrument. But for the focus of this session, I'm gonna focus on the later two. Especially, I'm gonna talk about several challenges we face between the intersection of the data analysis and how we interpret those data with theories, with simulations. So let's start. Let's say now we collect those signals. The first things we want to do is we want to search for the gravitational signals. You would hope that the signal just looks as beautiful as I show you at the beginning. There's a clear in spiral merger and ring downs part that you can identify. But in reality, this is what typically your data look like. The signal buried deeply inside the noise. So what we do is that we take a gravitational waveform template, let's say some waveform. We try to slide it through the data and try to look for a good match. If you really have a gravitational signal that lies inside the data, then this convolution between the waveform and your data should shoot up, the value should shoot up, or the signal to noise ratio should shoot up at some point at the right direction, or at the right location. So that is how we identify the location of these gravitational signal inside the data. So now the question is, then which gravitational waveform should you use? As we mentioned at the beginning there, different physical properties gonna change your waveform. For example, more massive systems gonna give you a stronger signal, as you can see from the bottom and the top, that's a comparison. These compact stars, they could also be spinning, and their spinning axes don't necessarily have to align with each other. And this misalignment of the spinning axis will lead to some precession inside the binary. And that kind of precession could, again, generate some difference. It's actually gonna generate that wobbling signal you see at the bottom. Okay? So what you want, what you hope for, is to create a gravitational waveform template bank that cover as exhaustively as possible all the parameter space so that you can search for the signal you're looking for. And that is not easy. Very often, these gravitational waveforms, they cannot be generated easily, either analytically or even semi-analytically. Very often, you have to rely on numerical relativity simulations to capture all the physics. Then that becomes expensive. You can only have limited number of simulations you can generate. So it brings us a question of then, how good do you want your waveform template to look like? And just to give you a sense, and by the way, we are doing better than this now, but just to give you an example, every dot here represents the gravitational waveform template we do have, like where we do have a template in the mass plane, because we have two stars, so it is two-dimensional, there are two masses there. And you can imagine for those areas where the template bank are sparsely populated, those are the area where you could, we do worse, we could possibly even miss the event. So this is our first big challenge. How do we construct a complete enough, and how do we define enough for the gravitational waveform template bank so that we can search for the signal we want? And especially if you are we might be able to look for all the typical, the majority of the events, but if you are looking for weirdo, then you might want to make sure you do have a good coverage for those exotic parameter space. Next, let's say now we already identify the location of the signal inside our data. Then the next things we want to do is to look into the details. We want to measure the physical properties of these gravitational sources. And what we do is that we take a Bayesian approach. We try to do some Bayesian analysis and to identify which gravitational waveform that has the parameters that best describe the signal. And as we just mentioned, to create those waveforms are expensive. So what we really do is that we generate some approximation methods to approximate those waveforms, and those methods are calibrated against numerical relativity simulations. So this process then brings us two-folded problem. You want to make sure your approximation method is good enough, and also the numerical relativity simulations you use to calibrate the approximation waveform are good enough. Otherwise, if any of these fail, you could introduce bias in your parameter estimation. And just to give you an example, this is an example parameter estimation result for the mass and the spin. The M and Q there, they are mass-related parameters. The chi is a spin-related parameters. What you want to look at is those blue contour. Those blue contour, they represent the case when your spatial resolution in your numerical relativity simulation are not enough. And that is a kind of bias you could introduce. And this bias grows as your signal-to-noise ratio events goes up. So what you see in this plot now, in the horizontal axis, going to the right-hand side, those are stronger signal. And the vertical axis is showing you how big this bias they could introduce for both the mass parameter, the first three, and chi, the spin parameters. This bias grows and becomes larger and larger as the events become stronger and stronger. And you can imagine, we just mentioned the upgrade of the sensitivity of our detector. That means we are expecting to capture more and more high signal-to-noise ratio events. And those strong events, they're going to dominate the information. They're going to dominate the science we produce from those events. So this problem is getting more and more serious in the future as our detectors getting upgraded. And we do want, as we mentioned, appropriate numerical simulation and also appropriate waveform approximation method that's efficient enough so that we can accurately extract those physical properties about the sources. Next, we just show you this kind of animation or cartoon at the beginning. We have already detected a lot of binary mergers, hundreds of them. Then that means we can start to do statistics. We can look at their mass or their spin distribution. We can even start to look into correlations between different parameters. So for example, we have already identified some correlations between the mass and the spin parameters with the events we detected in the first three observing round. Why do we want to do statistics? That is because of one core science we are trying to do. With this statistic, we can try to learn about the binary formation history. And just use the mass distribution as an example. When those binary, they went through different formation channel, they could give us different type of mass distribution. So ideally, we can take what you observe, which is on the right-hand side, and try to reverse the story and figure out which binary formation channel could account for what we observe, ideally. But in reality, the left-hand side is very difficult. It is very difficult to construct this formation channel. It relies on simulation and population synthesis model. And that is complicated. And to be even more complicated, different formation channel, they can produce similar distribution. There can be degeneracy. You can have more than one formation channels contribute to what we finally observe. So the story is very complicated. And that is the third challenge I would like to point out, which is how do we connect all these observed populations to the binary formation history? As we accumulate more and more events, we will be able to resolve those features in the distribution better and better. That is actually ongoing. That's what's happening. We might even identify more correlations between new correlations between different parameters. So how do we come up with a theory that can completely explain all these features? It's another big problem the field is trying to solve. Finally, let's come back to electromagnetic emissions. As we mentioned, a lot of this neutron star merger or neutron star black holes merger, they can produce electromagnetic counterparts, including short gamma ray bursts, kilonova, or maybe other type of EM emission as well. These EM observations, they could provide us with independent and complementary information about those gravitational wave sources. They are complementary to what we can learn from the gravitational wave side. So when you combine the information from both sides, you can do the best science. And just to give you an example, one parameters we are very interested in is the viewing angle of the binary. It is actually an important parameter for cosmological measurement. And the reason is the following. Let's say you have the binary. They are emitting gravitational waves. The emission of these gravitational waves are actually not isotropic. The emission is actually stronger along the rotational axis of this binary. So if you happen to be lucky, you observe the system from what we call the face-on direction along their rotational axis, then you would expect a stronger signal comparing to you observe it from the side. But on the other hand, how strong this signal are, if you get a stronger signal, it might just indicate that the system is close by. It's just a shorter distance. So you can imagine a case where you have a system, you observe it from the face-on direction, but far away, and they look identical to a system that is edge-on, but nearby. So those two cases I show you here. So without knowing which direction you are observing those binary, then you cannot measure the distance very well. And that is where the EMM observation can help, because from those EM observations, they can give us some constraint on which direction we are observing this binary. And then that will help us to break this degeneracy, give us better distance measurement, and therefore better cosmological measurement. However, what if this viewing angle you try to reconstruct from the EMM side is not accurate enough? We know that these EMM emissions are so complicated. We're still studying them. It still relies on a lot of theories and observation to interpret them. And it is not surprising to get some kind of bias in your estimate of the viewing angle. And that bias is going to then propagate to your distance measurement, then to your H0 measurement, which is the last things you want. And just to show you how serious this problem is, along the horizontal axis is exploring different level of bias in this viewing angle estimate. And that yellow arrow there is the simulated H0 value. So that is what you want to recover. And depending on whether you underestimate or overestimate this viewing angle, the blue band is what you recover. As you can see, just a few degrees of the bias in your viewing angle estimate could push your H0 value around by a lot. So that brings us to the last challenge I would like to point out. We do want to accurately interpret those observed EM signals, which is another big challenge. And there are certainly a lot more challenges in our field, but I hope I give you some taste of some major problems we are trying to solve. And let me summarize and come back to this timeline plot I showed you at the beginning. Right now, we are in the fourth observing round. We are talking about order of 10 to 100 of binary black holes merger detection every year, and also a few detections of neutron star, or neutron star black holes merger every year. This number is gonna grow by about 1 to 2 orders of magnitude as we push the sensitivity limits with our current generation of facilities. And then when we move on to our next generation of ground-based gravitational detectors, we are talking about basically all the stellar mass compact binary mergers in the universe. And that's gonna give us a lot more scientific opportunities, but also more challenges. And that is actually where the fun lies at. So I'll stop here. Thank you, and happy to take questions.
Space of, thank you, of simulations and the detections of the few gravitational waves.
Maybe, can you be more specific which slide?
Space of simulation, M1, M2, and all the dots.
Oh, that's kind of at the beginning, the template bank.
Yeah.
Yes.
So I have two questions. One is, I would have thought that this would be a really good problem for AI to use an emulator for the simulations. And then the other question is specifically about this plot. The region where all the detections are is underdense. Is that what you were hinting at, that you really want to fill in the space where things are more weird, and that's why you're filling in the bottom corner?
Exactly. That is our challenge. And I believe there are recent development along that line to populate this so that we can populate this template bank more efficiently. It's still under development. Yes.
We have one more question.
Thanks, very nice talk. What is the nature of the noise in the raw gravitational wave signal? Is it an additive noise, or is it a noise which is correlated with the signal, for example?
They are, I think we are all talking about instrumental noise, and it depends on the frequency you are looking at. There are different sources. Some of them can come from, you might not have enough photons, then that is some part. And some other regions, for the low frequency region, for example, it is a seismic noise, for example. So it depends on which frequency you are talking about. They all contribute. And that is why they look like that. Yeah.
More questions? We have time for 1 or 2 more questions. Okay, I have one actually. You were discussing about this line of sight when the neutron star mergers happen. What I want to understand is that, have you wondered whether the neutron star can actually be rotating in one particular plane, and after merger, the spin axis can change in some other direction, and basically the jet can come out? Then your line of sight measurements would be erroneous, right? How do you account for that?
Oh, so...
Like a spin flip of the resultant neutron star.
So if I understand your questions, the viewing angle we determine actually, we use the in spiral part to determine the viewing angle. So yes, certainly after the merger, they might get a kick and then go to any directions. So that is a separate.
That is separate, and that can be different as well.
That could be. That's actually something we don't measure very well. We do measure it, but not very well.
Okay, great. We have one question up here.
Thank you. I was wondering also about the template bank and away from fitting. If I remember correctly, I think people are indeed moving away from this, or for next generation detectors moving towards more AI methods or the machine learning methods. Do you?
Yeah, it is.
Do you know about this? Could you tell a little bit about the ways that people are moving away from this template bank?
That I actually don't know in details, because I think there are only several. I only have seen maybe not that many, like less than a handful of analysis existing so far. There might be more, but I think it is just starting. Yeah.
More questions? One more short question time. Okay, if not, then let's thank the speaker again.
Thank you.
Thank you so much for a very nice talk. Next up, we have a talk by Minia Mantiega. She would be actually discussing about disentangling stellar atmospheric parameters in astronomical spectra using GANs. Yeah. Just a second, the slides will come up.
Good morning to everyone. I am Minia Manteiga from Spain, and as it was told, I will speak about the use of GANs for stellar parameter disentangling and I will show in particular how we can do that with RVS Gaia spectra. So as we have already here in this focus meeting, generative adversarial networks are has been mostly used to infer parameters, attributes in images, and also to generate new versions of images. We think that this method is also useful to extract information from stellar spectra in particular. So I will show you how we have done that. So this is the summary of my talk. I will show you how the algorithm works, and I will also show you our framework, Gandalf, that we have developed to ease the use of these networks, and it's open to the public as a GitLab application. I will show you where. And then we will go through this application for Gaia RVS spectra. So at this point of the meeting, all of us are very well aware of that we are living in an area of big data astronomy, no? And especially we have a huge amount of images and also a huge amount of spectra coming from several surveys, some of them covering the whole sky, no? So we need it is mandatory the use of automatic methods to extract information about, for instance, stars in the Milky Way, to understand how the Milky Way has been evolving from the origins. And now that we already know that this evolution involves different episodes of merging that missions like Gaia has been able to show, to open this to the public. So we want also to obtain the greatest efficiency and accuracy in this extraction of information and optimize the use of computational resources for these huge amounts of data. Artificial neural networks has been classically used to extract information from spectra, and there are two main approaches for supervised artificial neural network, which are the classical forward modeling using synthetic spectra or models to train the networks and then to extract the information from the data. But there is also a different approach, which is called data-driven, when we want to use not synthetic spectra, but directly data for stars, which can be used as templates because they have a good derivation of their parameters, probably extracted from high-resolution spectroscopy. So we know that in an stellar spectra, the main information on the properties of the star is embedded in a complex way. We are talking about not only temperature and gravity, but also metallicity or even the overabundance of alpha elements in those stars. This information can be extracted, we think, in a better way using these generative models that also can allow us to understand how the information is really encoded in the data. So our goals with generative adversarial networks are several. The first, we want to compress the input data to a new representation that we call latent space, preserving the information, and this latent space has a very lower dimension when compared with the original spectra. Then we also want to maximize the information related to specific properties by entangling such information in the latent space while disentangling the non-relevant one. In this way, we will increase the accuracy in the parametrization, we will improve the computational efficiency, and we also can use the GANs to generate new samples outside the range of input data, extrapolate or interpolate our sample to maximize the possibility to extract information. So let's have a look to the algorithm. Generative adversarial networks are composed by two types of networks. We have already been told about this. One of them is a classical autoencoder, which is composed by two networks, the encoder and the decoder. And the idea is that they input the original spectrum and with the objective to map the original spectrum at the end, at the output. And by doing that, they compress the information in a lower dimension that we call latent space. The other networks are called the discriminators. They can be 1, 2, or how many parameters we want to entangle or disentangle. And the objectives of the discriminators is to predict a parameter using as input the latent space, and that was obtained by the autoencoder. This parameter is produced in a range of possible values in bins. So we discretize the possible values of every different parameters, and what we really obtain is the probability of a value between this range. These two networks are concatenate one with the other in the following way. Well, for input, we enter, the encoder receives the spectrum and also the stellar parameters and produce the latent space. And then during training, the discriminators try to predict the value of the different parameters. But the task of the decoder at the end is to obtain again the spectrum as close to the input as possible. No? The discriminator tries to predict the astrophysical parameters in a way that their errors are used during training to teach the encoder to fool the discriminator by removing the conditional parameters from the latent space. So the discriminators produce the parameters, but their errors are used by the encoder so that the presence of those parameters in the latent space is minimized if we want to disentangle those parameters, and maximized if we want to entangle them. So the autoencoder objective is modified not only to achieve a correct reconstruction of the original data, but also to try to maximize the errors of the discriminator. And how is it done? This is done by the computation of the total loss function of the system, of the network, which is the difference between the loss function in the reconstruction by the decoder of the spectra minus the loss function of the different discriminators. So over time, this methodology compels the autoencoder to expunge those intrinsic features of the original data from the latent that the discriminator endeavors to predict. If we use positive values for the lambda factors in this computation of the global loss function, we will try to disentangle the parameter from the latent space. But if we use negative values, we will entangle, because the last function that aims to be minimized will entangle the value from the error from the discriminators. We use the mean square errors as the loss function for the autoencoder, and we use the cross entropy for the discriminators. So at the end, this works producing a latent space where we have a lower dimension and we have entanglement or disentanglement on specific parameters that has been computed during the generation of the latent space. To make it user-friendly, we have developed a framework, which is, as I told you, in GitHub. It is quite easy to use, and it is composed by several Python classes to generate the data, to pre-process the data, normalize, etc. Command line tools to define, train, and test the models, and a web application to show how the algorithm works in a visual way. So you can visualize not only the spectrum, but also the latent space, and make the changes in the parameters and see how it goes. So let's see the application to Gaia RVS. Maybe you already know, Gaia is the mission, the spatial mission of the ESA that is mapping the stars in our galaxy. It is producing astrometry of very good quality, but also is producing spectrophotometry for all the sources in the skies. For the moment, 2,000 million stars. And in the case of the brightest stars in the galaxy, it is also measuring radial velocities by obtaining these near-infrared spectra from the RVS spectrograph. In DR3, the third release of Gaia, they were published 1 million spectra for stars. And these are the ones we are going to use to test this method. So to do that, we use a data-driven approach. We select a sample of about 64 million stars with atmospheric parameters very well determined from high-resolution spectroscopy. This is the distribution, of the stellar parameters in the sample. We change a bit the architecture of the GANs, not to enter the parameters as input, but for the latent space. And to test the effectiveness of the disentangling, we use this TSNE clustering technique that, as you know, it has been already mentioned here, it projects the spectra, in this case, in a two-dimensional grid, so that stars that are quite similar are close together. If you label this clustering according to temperature, gravity, methallicity, etc., you will see that this labeling is quite coherent, because temperature, gravity, etc. are conditioning the shape of the spectra. So you can check the entangling or disentangling using this clustering. So to use I will finish in 2 minutes. To use the Gandalf for the disentanglement, what we did first is to derive an optimized data representation. We use pure latent without entangling or disentangling, and 2 levels of entangling, disentangling. A first one, entangling information about chemistry, metallicity and alpha elements enhancement, and disentangling physics, temperature and gravity. And the second disentangling was the other way around. So if you see the clustering in the first panel on your right, you will see that temperature and gravity, the first panel is the original spectra. The second one is the latent signal. And we label according to temperature, gravity, metallicity, and alpha elements. You see that temperature and gravity in the first case is completely disentangled in the latent space, because the points are all mixed around. And in the second case, it was the chemistry which are disentangling. So the technique is working properly to do disentangling and entangling. And what we do is...
I think you should wrap it up, please.
Just, this is the last one. To use this latent space to do stellar parametrization, instead of using the spectra directly for normal generative, for normal regressors, we use the latent space and obtain better accuracy in the derivation of temperature and gravity when we use the disentanglement of chemistry in the spectra, and we obtain better derivation of the chemistry when we disentangle the physics of the spectra. And just to prove that it is right, I show here the Kiel diagram for those stars and the metallicity alpha diagram. And that's it. Thank you.
Thank you. Thank you. I think we have just one small question. That's it, if it's there.
We can talk later if you are interested.
Talk with the speaker later. I think, thank you. Thank you so much for the speaker. Yeah, exactly. The next talk we have is an online talk. It is by Priyanka Jalan. Priyanka, can you hear us?
Yes. Can you hear me?
Yes.
I'll share my screen.
No, I think there's some technical error. Priyanka, can you hear us?
Yes, I can hear you perfectly. Can you hear me? Hello.
Yeah, Priyanka, can you kind of put your screen, share your screen?
Yes, I'm sharing my screen. Are you able to see it or? Hello. Hello.
Just a second, Priyanka, we are setting it up. Thank you so much for the speaker. It's very nice. The next talk we have is an online talk. It's deja vu.
Yes, I can hear you perfectly. Can you hear me? Hello.
Priyanka, can you there's a problem there.
Are you able to see my screen now?
Okay.
Hello.
Shall we?
Are you able to see my screen now?
We can hear you. Just a second. Priyanka,
Hello.
shall I?
Hi, Priyanka, can you hear me?
Hello. Hello, can you hear me?
Okay.
Yes. I can hear you completely fine. I don't know whether it's a problem from my side. Yes, I can hear you. Do I need to do anything?
No, you're fine. You're sharing your slides on Zoom. We're just trying to get your slides up onto the screen.
Okay, great.
So if you can share, can I plug in my laptop?
How much time will it take? We can go to the next speaker and.
No, we can't. We can't.
I'll quickly finish it. I'll finish it within 10 minutes. But
No. You're okay.
okay.
If not, should we switch to the video?
Uh, okay. I mean, yeah, you can also display the PDF I have sent. So
No, Priyanka, now we can see you and we can see the screen and everything is fine now. Priyanka, sorry for the technical trouble. So just to. No, I think it's fine. So next speaker with us is Priyanka. Priyanka is gonna talk about flame fitting Lyman alpha absorption lines using machine learning. Priyanka, you can start.
okay, great. Uh, Thank you, everyone. So I am Priyanka Janan. I'm a postdoctorate at Center of Theoretical Physics in Warsaw. And thank you, organizers, for giving this opportunity. I'll try to keep it within the time since we have lost some time for the technical difficulties. I'm going to talk about my recent project, which is in press in A&A, but you can see the archive version here. And the title basically comprises of two parts. The first. I'll finish it within 10 minutes. Oh, I think there is an lag between the. Okay, I mean, yeah, you can also display the PDF I sent. So.
Now, Priyanka, now we can see you and we can see the screen and everything is fine now.
Um, Sorry, I think there is an lag between, and I can hear. Hello everyone, my name is Priyanka Jalan and I'm currently a postdoctorate at Center of Theoretical Physics in Warsaw. First of all, I would like to thank the organizers for giving this opportunity. And today I'm going to talk about my recent work, which is in press in A&A, and you can see the archive version here. And the title comprises basically of two parts. The first part is the Ramirez absorption lines. So these are the absorption lines that is coming from the neutral hydrogen prism. Hello.
And I'm currently a postdoctorate at the International Astronomical Union. First of all, I would like to thank our advisors for giving this opportunity. And today I'm going to talk about my recent work, which is in Princeton AMA, and you can see the archive version here. And the title comprises basically of two parts. The first part is the laminar flow absorption lines. So this is the absorption line that is coming from the neutral hydrogen present in the intergalactic medium. A medium is basically whatever is present between the two galaxies. So the imprints of this neutral hydrogen can be seen in the spectrum of the quasars, and the part which we are interested is in, called the laminar absorption lines. And we are going to fit these absorption lines using machine learning. This project has been done in collaboration with Vikram, Vivek, and Prakash. So now I'm going to talk about this model, which has an acronym called FLAME. But before I go to the model part, let's talk about the brief introduction about the quasar spectrum and the laminar absorption lines. We know that the universe is being expanding, and therefore all the wavelengths that are emitted by the quasars are redshifted. Now, dependent on the presence of a cloud, of the neutral hydrogen cloud, dependent on its column density, where the cloud is located, and what is the temperature of this cloud, we do see an absorption in the continuum of the spectrum of the quasar. So here's an artistic image for that. You have the quasar spectrum, which is basically the continuum and the emission line that is coming from the quasar. And whatever is present in front of the quasar to the observer line of sight, we see it as an absorption in the spectrum. And you can see here that dependent on where the clouds are located, so the redshift, the column density, and the temperature of the cloud, we see different types of absorption lines. So the lines which I'm going to talk about are the lines, the laminar absorption systems, which are present in the spectrum of the quasar and typically in the region called the laminar forest. That, as the name says, it's a forest because you have so many multiple lines, and it's the region between the laminar beta and laminar alpha emission line. And if I zoom into this particular part or any part of the laminar forest, this is what the laminar absorption typically. Absorption lines can be well defined with a profile called Vogt profile, which is a convolution between the Gaussian and Lorentzian profile, where the central part is mostly dominated by the Gaussian, and the wings are mostly dominated by the Lorentzian, giving us this Vogt profile shown in the green. So once we know that that this fitting can be done by a Vogt profile, it comes to the question: why is it important to study to fit these absorption lines of the intergalactic medium? It's because the column density and the Doppler width, which is represented by the B and N space, is a proxy for the temperature and density of the intergalactic medium, respectively, and therefore it gives an information about the equation of state of the intergalactic medium. Here I'm just showing an example by Zhang Ben's paper, where we have taken this image showing 3 column densities ranging from 19.5 to 20.62. This is on the higher side of the laminar alpha absorption, going to the laminar limit systems and the dam laminar alpha systems. But I'm not going to the detail, but it's just to show that how the profiles look like on a real data. And once we fit these absorption line, we can get the temperature density, we can get the evolution with the redshift, and therefore understand about the universe or the expansion of the universe in general. So now we understand that this provides information about the intergalactic medium. But the question again comes: why we need the CNN or why we need machine learning? The answer lies in the spectrum of the quasars. As I've shown before, a redshift 3 quasar spectrum, which is this one. But now if we see the spectrum of these quasars at various other redshifts, so ranging from 0.4 to 3 to a redshift 6, we can see there is a difference in the quasar spectrum. On one hand, at a very low redshift, we have very countable number of absorption lines, although there are still many, but even in for talking about a single quasar spectrum, we can still count the number of absorption lines, the laminar absorptions. The point here to notice, the other point here to notice is that because it's a low redshift, the laminar alpha forest shift to the ultraviolet regime, and therefore the spectrum is taken from Hubble Space Telescope. Whereas if we go to a redshift 3 quasar, the lamina profiles shift to an optical regime, and therefore it is taken from ESO. And you can see the spectrum of the quasar here, and you can see the number of absorption lines, which have quite increased a bit compared to the redshift 0.4 quasar spectrum. Now, if we go to a redshift 6 quasar, the continuum is totally absorbed by the renewable hydrogen content present in the intergalactic medium. And therefore, what we see is that even in one single quasar spectrum, we have numerous such absorption lines that needs to be fitted to get the parameters. And in the era where we have SDSS and DAISY data, fitting them using manual codes or semi-automated codes is just computationally expensive. And therefore, we use machine learning for this purpose. In this work, I'm going to talk only about the supervised machine learning and talk about both classification and regression in this case. But if I have also worked on unsupervised machine learning, so if you have any questions, do contact me on Slack. So let's talk about the problem in hand. So we want to fit these absorption line and get the parameters. Therefore, we need some training data set, the data set which is labeled. But in the real case scenario, we do not have such data set that is labeled. We do not have enough number of such training data set, and therefore we rely on simulated data set. So for a given column density and velocity and the Doppler width, we simulate these absorption line profiles. However, in the previous case, you have seen that how the real data actually looks like. This simulated data looks more like the fitting, but not the data itself. So therefore, we make the simulated data as real as possible, and therefore we convolve the simulated data set with the line spread function of the HST spectrograph, and that's the green part which is showing here. So the dashed line, as you can see, much more clear in the case of double lines, are the simulated work profiles. Then we convolve them with the line spread function, and then we add the noise. So this is this red distribution is the training data set now, and it is much more closer to the real data set. While we are talking about HST data line spread function, because in this work we are only going to talk about the low redshift quasar spectrum and not about high redshift. And because we are going to talk only about low redshift, we have only considered single and double absorption lines and not much more complex systems. Because the 90% of these data, which are going to talk about in the later slides, are either single or double lines. So this is the training data set, what it looks like. So we have millions of such single absorption lines and millions of such double absorption lines. Now the model contains two parts. The first part contains classifying these lines as single or double, and then identifying the parameters. So in the case of single line, there would be only column densities and Doppler width. But for the double line, there will be two column densities, two Doppler width, and there will be a velocity separation between these two lines. So this is the classification model. We have used a CNN model. We input these training data set to this model, train it. Of course, we modify the hyperparameters till we achieve a very good classification accuracy. Again, have a look at the paper if you're interested in the model and to contact me. So I'm not going into the details of the model, but let's talk about the result part. So once we input this training data set of single and double lines to the model shown in the previous slide, we get this confusion matrix. And we have an accuracy greater than 93%. I'm showing some examples, two examples of each class in the right panel. These are the true single lines which are also predicted as single line, and the true double lines which are also predicted as double lines. And you can see the examples are showing visually as well. But for the cases where the single line are identified as double line are generally the cases where we have low signal to noise ratio. However, for the cases where we have double lines predicted as single lines, either both of the lines are very saturated and they have very low velocity separation, or there is a very small absorption line, very low column density line paired with a very high column density profile in a low signal to noise ratio data, which is identified as a single line. So visually as well, we can see that there is the false negatives and false positives visually as well. So once we have identified, we have trained a model for identifying the number of line. We then train them this data again using the same input for identifying the column density and the velocity width. So here's an result for single absorption line profiles. We show that the typical true versus predicted line here for the column density and for the Doppler width here. And you can see that they are following the one-to-one line, the black line here. We also show in the upper panels the true minus predicted values, and they are centered at 0. And we also show the 90 percentile and the 68 percentile in the paper as well. We show an example here of a signal to noise ratio 14, which you can see that the true and predicted values are pretty consistent with each other, and you can see the residual in the bottom panel. So then we do the same analysis for the double absorption lines, and again for the test data we can see this following the one-to-one line. Of course, in this case we have a little bit broader distribution of the column densities in the case of double lines. So now once we have done it for the simulated test data set, we now apply this model for the real data set. And from Danforth paper, we have around 1500 single and double absorption lines combined. And therefore, we use a semi-automated code named Viper, and we fit these absorption lines. So we have the fitting from 3 methods now. We have a manual fitting, we have a semi-automated code, and then we also have a fitting from the machine learning. What we found is that when we are using the machine learning, the accuracy slightly reduces compared to the other methods for the real data case. And to identify what was the problem, we create a mock data set. So the mock data set is now basically the simulated data set for the exact same parameters as the real data set. And here I'm showing 2 examples of a single and double line. And on a visual purposes, it seems that it's doing a pretty good job. We have but there still is difference, because when we do the same analysis for the mock data set, we find that the accuracy is increased. One issue which we found that could be causing this discrepancy is the correlation between the errors in the real data, which is not present in the simulated data set. However, given this, we identify the parameters BNN distribution for the real data set, and what we found that the BNN distribution is quite similar with the other methods, which was the goal. And we can see here that from the D16 and Viper page, Viper analysis, we have the solid distribution, and this work is shown in green. Also for the mock distribution, we show in the dashed line, and which is pretty much consistent in the column density and Doppler width distribution regime. Just to show a few example of failures for the people who are just starting in machine learning, we do get initially these plots, and it's after we have taken into account that there is no overfitting, the hyperparameters are tuned, we get a very narrowed distribution of true versus predicted. So I'll just end up my slides here with the summary page. Just before the ending of the talk, I would like to promote my website where I make a digital art for your science project. Of course, there are AI existence, but if you ever feel like you need a human touch for the digital art for any science project of yours, do contact me. Thank you, everyone, and I'll leave to the summary page and ask for any questions if you have any. Thank you, everyone.
Thank you. Thank you, Priyanka, for a very nice talk. I'm sure many people have questions, but due to pressing of time, we would request everyone to kind of contact you on Slack or on the web page that you have listed. Thank you so much, Priyanka, for your very nice talk. Now we go to the next speaker. This is Adrian Top. Adrian is going to talk about synthetic survey catalogs for the Galactic Roman Infrared Plane Survey GRIPS using Pyanake. Adrian, the floor is yours. Hi, everyone. Thanks for coming, and thank you for the organizers to give me the occasion to talk about our work. I'm Adrian. I'm a postdoctoral researcher at the University of Pennsylvania, working with Robin Sanderson. And I am going to start by just mentioning that my background is rooted in the analysis of cosmological simulations. This background is actually a rendering taken from the Eagle simulation. And for those that are unfamiliar with the field, please come tomorrow to Yopshe's invited discourse in the afternoon. A lot of the simulations are made to study galaxy formation, and on that aspect, the Roman Space Telescope will be a revolutionary facility for making progress on that field. For a bit of a reminder, for those that are not familiar also with the instrument, the Roman Space Telescope used to be called WFIRST until kind of middle of the pandemics when it was renamed to honor the former Chief of Astronomy of NASA and also mother of Hubble, Nancy Grace Roman. It was originally developed as a response to the US 2010 Decadal Survey as a recommendation to have an instrument to study dark energy, but kind of like now expanded towards a lot more different fields, from the study of exoplanets to the study of galaxies, also just stellar population, but also detection of gravitational waves to the detection of supernovae. The target launch is going to be October 2026. They are apparently on track to achieve that, which is great and awesome, but also put a lot of pressure in terms of time expectations. It's going to be equipped with two instruments, but the one that is probably the most important for our work is the wide field instrument. This is truly really where Romans advancement is going to be lying, because of how wide the field of view is going to be available. You have to understand that we have like 100 times the field of Hubble that's going to be accessible on a much faster pace. So in terms of efficiency, it is unprecedented. There are lots of range of science that couldn't be accessible before, and this is going to be done through multiple surveys. There's 3 core community surveys that are organized by the Roman collaboration itself, such as highlighted to wide area, from highlighted to time domain, but also galactic bulge time domain. But there's also 25% of the time that will be dedicated to general astrophysics survey, of which the very first that has been actually announced back in January is the Galactic Plane Survey, which our work is going to be preparing for this. There's been also a selection of different wide field science teams that has been done a year ago. And in those teams, we have actually our team, the Roman Infrared Nearby Galaxy Survey, which is dedicated to prepare data sets and pipeline to prepare us for the ability of Roman to survey star populations in nearby galaxies up to about 15 megaparsec. The reason why I'm mentioning this team is also because the Galactic Plane Survey will have certainly a common enemy in what is crowding and how we can actually understand it. This is really what we want to understand with our team, and with the Galactic Plane Survey, we're going to also need to actually understand crowding better. To that purpose, we have a pipeline that we developed with RINGS, which is essentially a sort of a test bed pipeline where we can test commonly used photometric routines. The way the pipeline works is that we take a galaxy model entry, we run it through Pine-Walter to produce synthetic star surveys, and then we create mock images from the synthetic star surveys with STIPs, and then we actually test our various routines to see how we can produce reduced photometry from it. The pipeline that's important today I want to talk about is PineNK. It's a pipeline we developed with Robin that is available online that you can use. It's dedicated to produce synthetic star surveys from cosmological hydrodynamic simulations data. And it was originally developed from the IAU framework that was published by Robin in 2020. IAU was this work where Robin and her team produced synthetic star surveys a la Gaia DR2 in using fire simulations, using 3 different fire simulation, using 3 different observations in the simulations to have some sort of like mock Gaia data. What we did with PyNK is that we improved upon this framework by first turning NNK, which was made of individual Python and C++ routines, which was really hard to actually integrate into various pipelines. We turned it into an actual Python package that can be easily installed. We also expanded the sets of different photometric systems that can be simulated with it. It used to be Gaia only, but now actually we can do Roman and a range of other photometric systems, and where the framework itself was really hard to be able to debug or expand because of the way it was developed. Now we actually have a modular implementation that makes the work easier for me for upgrading further. And here you can see actually some of the original NNK flux maps that were produced by Robin in 2020. So PyNK itself, what it does is that, as I mentioned, it's turning the galaxy simulation into synthetic star surveys. It's doing that in 2 steps. The very first step is actually to wrap around the Galaxia software that was developed by Sanjit Sharma. What Galaxia does is that it takes the particle data, so you have mass in the particles, you have various position and velocities, and what it first does is to estimate densities from this position and velocity in the phase space. And it samples the phase space using those densities. It samples the IMS using the mass from the stars, and it produces the first sets of synthetic stars. And then using preloaded isochrones for whichever photometric system that has been selected, it will interpolate the isochrones to produce the mock photometry. We get from this a first mock catalog that is ideal, doesn't have any sort of extinction or all. And in the second step, we do some post-processing work on this mock catalogs. The one that is going to be most important for today is the extinction driver that we have. We take a dust model that is extrapolated from the simulation gas content. From the gas content, we assume a metallicity to dust ratio, and we produce line of sight column densities from the observer position to each particles, and we interpolate over. And then we have some extinction coefficients to get this extension and redlining. Once we have this, we get our actual synthetic surveys that I'm going to be showing further later. And just to illustrate how easy it is to use nowadays, read this little snippet of code is just 2 lines. The hard work is on the P, the very first argument that is given to the NNK object that contains all of the simulation data. So to produce an actual galactic plane survey, there was a white paper published by Roberta Palladini and her team in 2023 that suggested some specifications about how to produce a galactic plane survey using Roman. The key specifications, I've listed them here. The thing that I wanted to mention is that what PyNK also allows us to do is to limit early on, before running Galaxia, the color magnitude diagram box that we want to limit the production of synthetic stars from. Because if we actually don't limit that, if we don't give a high limit on the magnitude, we end up producing a very large amount of very low mass stars, which would be a waste of resources. And that will be important, you'll see later on why. In this case, we're actually using 25.3 in the 158 filter of Raman, and we just putting that in pre-processing, and it's in post-processing later on that we actually put all of the other specifications. To understand this better is that out of PyNK, what we get first is an actual all-sky survey. We're not limiting the galactic plane itself out of the first output of PyNK. And so on the left, what you can see here is actually that old sky survey that I was mentioning. So you have 2 flux maps. On the top, you have the flux maps simulating Gaia DR2 photometry. And in the bottom, you have the flux map simulating the Raman photometry. What I'm showing here is a prototype 2% survey. There's logistical challenges that we need to accomplish to be able to do what we want to achieve down the road, which is 3 different simulations using 3 different observer positions. When I say 2% survey, I'm saying that it's actually sampling the IMF and the phase space in a 2% way, so it's representative overall of what the 100% would be if we were to just randomly pick each star and multiply them. So those flux maps here show you 2.4 billion stars, and you can already see the difference between Gaia and the Raman bands here. Gaia is optical, Raman is going to be near infrared. The near infrared will really pierce through the dust lanes and be able to have like a lot more populations on there. On the right, you have collimated diagrams using extincted and radon absolute magnitude. So it's simply the apparent magnitudes removing the distance modulus. And you can see actually also the effect of reddening and extinction there. On the right, those are the Raman. On the left, you only have Gaia DR2 and LSSC optical. In the contour maps are actually what the Raman heat map would be spreading onto the collimated diagram if we were to include them here. And we wanted to understand a bit better actually those populations that are hidden behind, that are actually accessible to Raman, that were not accessible to Gaia and LSST. The top showing all of the stars that are only in Raman and Gaia or LSST, and on the bottom are those are only in Raman. Those are in this case unextincted and unreddened absolute magnitudes. So now actually we're removing extinction effects to understand better those stars. And you can see at the bottom that we have a large population of very low mass stars, like this sort of blob that you see at the bottom, around 10 in magnitude. But there is also like a nice spread across the main sequence and the asymptotic giant branch that is about the same. Those are just stars that are hidden behind the dust, essentially. So this is a work in progress. As I mentioned, it's a 2% survey. It's 2 terabytes of data. If I want to achieve 100%, it's going to be 100 terabytes of data. We have a lot of work that we need to continue to actually improve upon. We want to include also Gaia DR3, replace Gaia DR2 with Gaia DR3, and include Euclid as well. The main thing I want to be able to work on is, as I mentioned, producing various simulations, various observer position, notably potentially having various observer position that would be carefully selected to be on the rim of a spiral arm or in between 2 spiral arms to see how that would differ in the final simulation. So thank you very much for your attention, and I welcome any question.
Thank you. Thank you, Adrian, for almost finishing on time. We have time for questions, 1 or 2. No questions. Yeah, there's one there.
Thank you for a nice talk. This might be a naive question because it's kind of outside of my field, but it's very interesting to see all these different surveys now achieving results stellar populations. I was wondering if you can also apply this in the future to ELT and, just kind of pile on maybe even JWST data. So is that kind of the goal, or are there many different codes similar to this that do kind of a similar work of trying to create this kind of code to tackle these results that are populations?
Yeah, that's a good question, and actually this is the goal eventually, to have the software available and easily tweakable by just changing a few arguments in it. JWST's isochrones are already loaded in PyLink, so it is possible for JWST. Not ELT, we don't have those isochrones yet, but once we have them in, it's just a matter of preloading them and then producing the simulation itself.
Very cool.
Thank you. Any further questions? If not, then let's thank the speaker again, Adrian, for a nice talk. And we go on with the last talk of this session. It's Robert Feldman. Robert is going to talk about accelerating the computational modeling of cosmic gas with deep learning.
Thank you very much. And welcome, everyone. I know I'm the last talk for lunch of a special place. So before I start, I'd like to say that a lot of the stuff I'm showing today is work done by my former PhD student, Mauro Bernardini. And I want to highlight his work, so his contribution, but also the contribution of other people at the University of Zurich, as well as in the FIRE collaboration. Okay, so so the motivation is as follows, right? So we are interested in answering questions in astrophysics and cosmology, and often we do this via tracers that are available to us, right? And one of those tracers is, for instance, the 21 centimeter kind of signal, so the 21 centimeter signal is affected by all sorts of kind of physical processes that operate in galaxies, in the also intergalactic medium, etc. And so we have essentially two choices. We can either say we essentially marginalize over these uncertainties or these astrophysical processes. We can approximate them to some sense away. So once we go to sufficiently large scales. But if you really want to go to relatively small scales, then there's no way around it. We have to try to model them to some extent. And there are different ways of doing this. Obviously, so from somewhat kind of simpler approaches to something that is more, that really tries to really involve or fold in all the different processes. So why do we care about the small scales at all? There's actually a lot of kind of good information, contained on small scales, also for cosmology. So that's one reason. The other reason is, of course, that there's also this coupling. So the small scales do affect the large scales. So it's quite interesting actually to learn about this. And then, of course, very kind of naturally, we also want to learn about the astrophysical processes themselves. So we, for instance, want to learn about galaxy formation or how gas flows into galaxies, or in the CGM, how the metals flow out, etc. Okay. Now, so if you want to model the baryonic physics, galaxy formations are, let's say, the most principled approach to do this. We can, in principle, add all the physics we want, all the physics we believe is important, and then see what happens, right? And that sounds great. There's, however, one big kind of problem with this. Doing this is very computationally expensive. And so the idea is that we can use simulations and somehow encapsulate their results into neural networks. So essentially, we generate surrogate models, also called emulators. All right, so the idea is that once we have our neural network and essentially it's trained to reproduce the result of a simulation, we can then rerun it, maybe on a slightly different kind of circumstance, to make predictions. And so, for instance, we can use it to generate large mark catalogs with the physics that's essentially encapsulated now in the neural network. We can also try to extrapolate. That's obviously a bit dangerous to do, but we can try to do that. Maybe better is to interpolate. So, for instance, if we have simulation snapshots at different redshifts, but maybe only at relatively coarse snapshots, we can now try to interpolate to, let's say, redshifts in between those kind of snapshots. I mean, the main point of this is that, the emulation is very, very fast. So essentially, kind of running one of these simulations, this can take months of wall clock time on a supercomputer. And once the neural network is trained, the actual application can only, this can take seconds. Okay, so we can in principle make predictions in seconds, and that can be very useful, for instance, if you want to do something like SBI, also called likelihood-free inference. Two other good applications are that fall in this regime is that we can try to do so-called super resolution simulations or inference, meaning that we can try to so we have a low resolution image, let's say, or a map, or maybe a three-dimensional data structure, and we can try to increase the resolution. And again, this is based on information that is in our neural network that is trained on simulations. Another thing is, what we can do is we can try to combine information that we have from different simulations, such as from, let's say, cosmological volume simulations that maybe, let's say, they capture, well, let's say the small scales, and zoom-in simulations of very massive halos to really learn more about all the different environments of these galaxies or these halos, you know, different cosmological environments. And this is then kind of useful if you want to make, essentially want to upscale our simulations. We can essentially take a large cosmological volume and then apply our baryonic modeling on top with the help of deep learning to make predictions for these larger scales. Okay, so this essentially is the basic idea of this. So now I want to introduce the framework that we have developed, and it's called EMBER, stands for Emulating Baryonic Enrichment Framework. And the basic idea here is that we want to have a framework that predicts the distribution of gas surface densities for a given dark matter surface density. So essentially, it allows us to paint on gas onto dark matter maps. Okay, so the framework that we have developed is, so it works on maps, so it's two-dimensional, but in principle, I mean, we're thinking of going to 3D in the future. So the basic idea is that it's a CNN that is coupled with a discriminator, so it's a GAN, so it's CNN plus GAN. And the CNN essentially has a unit structure, so for those of you who know what I'm talking about. So it's trained on cosmological hydrodynamical simulations, and so the basic idea is that we have, let's say, the dark matter field here shown on the left, and then we have also the gas field that's shown here on the right, and during training we learn the mapping from the dark matter to the gas. And then we can do this in principle on different resolution levels. So we can, for instance, also learn to make predictions from a low resolution dark matter simulation to a high resolution gas map. So that's shown here at the bottom, in the bottom row. And then we can take a, let's say, comparably low resolution but large volume simulation, so it's dark matter only simulation. And then we can apply the neural network to make predictions for how the gas is distributed in this whole cosmological volume. Yeah. Okay. So just the simulations that so we are using as our training set. So these are simulations from the FIRE collaboration. So they run with Gizmo and they run with FIRE2Physics. So we use two different kinds of simulation really to cover different environments, as I alluded to earlier. We use a cosmological volume simulation that's called Firebox. So that's the first cosmological volume simulation with FIRE2Physics. And then we also use zoom-in simulations of massive halos to cover massive halos, because these ones are lacking in the cosmological volume that we have because it's relatively small. So what's nice about it is that these two simulations, or these two different sets of simulations, they are kind of similar in numerical resolution, and that's why we can essentially kind of easily combine them together. All right, so the basic idea is as follows. We have our, let's just focus now on the box. This works similar for the zoom-ins. So let's say we have a box here on the top left. So we slice it into different, so we create these slices. So the box, as I said, is about 22 megaparsecs wide, and the slices are about 1.2 megaparsecs thick. Okay, so we have these slices. Then we project the matter fields, either the gas or the dark matter, in these slices. So we create the maps. And then we extract tiles. So we use the training actually, so this happens on these relatively small tiles. And so we have essentially now tiles that are matched. So we have a dark matter tile and the corresponding gas tile, and that's what the neural network will see to train. All right, so as I mentioned already, EMBER is a GAN, but it is a conditional GAN. So the conditional component here is the dark matter field. So again, was I think explained already earlier, so I don't really have to talk about it. This is just a schematic. For the aficionados, so we use a fully convolutional generator, as I said, it's a UNet with noise injection and the dark matter maps as conditional input. And we have, so you have to think about the normalization scheme. So how do you actually represent the data fields internally? So what we're using is this kind of log transformation here that I'm showing here. And then the cost function is perceptual loss. But that is actually only used very initially during the training because we have a GAN, right? So we essentially have the adversarial loss that will take over also quite quickly during the training stage. Yeah, we also actually, so this version of Ember is a Wasserstein GAN. So we actually, so the critic is learning the Wasserstein metric as well. Okay. So let's see how well it works. So here I show you an example. So this is so one of the slices from Firebox. On the left, you show the dark matter field, and different rows are different zoom-ins. I zoom in a bit more, and then on the right, I show the H1, all right? So the atomic hydrogen. And this is what a kind of unit would give you, essentially just a CNN without the GAN component. So it's a deterministic network. And it does kind of reasonably well. It gives you the average right, but it doesn't look realistic, right? It misses all this. So you don't have all these fine features that you're supposed to see. And then Ember gives you this, okay? And here I show 3 different realizations. We can, of course, kind of produce as many realizations as we want, because the goal is not to predict the average. The goal is to predict the actual distribution, right? So we can essentially sample from the probability distribution. Okay, and I'm not sure what happens now. Here we go. I also have a few more plots. So for instance, if you want to look at the power spectrum and the bispectrum, or if you want to, let's say you measure how much gas map is within the circular apertures that are the size of the real radius. If you look at these kind of statistics, they all look reasonably well. It's not perfect. So I mean, accuracy is whatever, 10, 20%. So depending on what you're looking at. One issue with Ember is that the training is still comparably expensive and we only have a single output. Also, the training is only for a single redshift, so that's bad. So that's why we have essentially Ember 2. That's now multi-redshift, multi-scale, and multi-field. It's also a slightly different architecture, so it's kind of faster and has fewer weights, so it's easier to train. And I don't have time to tell you how this works, but I want to show you what comes out. So here, for instance, I show you the H1 column density distribution functions. The lines are the simulated ones from simulation, right? And the shaded areas are the emulated one. It looks well. And here we can essentially make predictions for any redshift we want. Here I show you density temperature distribution. Again, we can essentially make predictions, so not just for individual fields, but also for the correlations between the different fields. And it looks reasonably well. It's not perfect, especially at low redshift. It gets harder, but this is also because our box, is small, and this is more of a problem at low redshift than a higher redshift. Here, for instance, I show the dark matter gas cross correlation. All right, that's my summary, and I'm happy to take questions. Thank you.
Thank you, Robert, for taking us through Ember. We have questions here. Sure.
So this is a question that I ask everybody who's using surrogate models. What's the level of fidelity do you need, and how do you validate that you have the level of fidelity that you need?
Yeah, so that's good. So that's why we essentially create plots like this. This depends a little bit on the question of what you're trying to do with this, right? So for instance, if you want to use it to estimate power spectra, then that's your essentially quantity that you have to compare with, right? So you want to say, okay, so plot the power spectrum and see, okay, it's accurate within 10%. And that's of course always done on a separate test set, right? So it depends a bit on the application of what you want to use the code for.
It basically boils down to level of fidelity, because I mean, the training can go wrong too, and training can introduce biases, etc.
Yes.
And so it's a question of how do you protect yourself against those things happening.
Yes, so you always have test sets, the halted sets on which you validate your training. I'm not sure so this if this doesn't answer your question, then it's maybe better if you talk afterwards.
Okay, one short question, anyone? Yeah, please.
Thank you for great talk. So the one question is like, what's the limitation of the number of box cells or data cube in this machine learning model?
Sorry, so can you repeat this again?
What's the limitation of the number of box cells?
The number of voxels.
Yes.
Okay, so we don't, as I said, we don't actually use voxels here because it's maps. So it's really pixels.
So you mean 2D data?
Yes, it's
okay.
maps. Okay,
Maps.
I mean it's slices, so you can in some sense you can still kind of make a 3D prediction because you can do essentially a tomographic approach, but it's slices. And it's maps based on slices. The pixel size, so for EMBER-1, that was essentially, we wanted to not you have more than 512 by 512 as our input, so that was essentially given by that. We want to go as fine as possible, and so in EMBER 2.0, this is something that is still in prep, which is this kind of multi-scale approach. We want to essentially allow to go to arbitrary high resolution. I mean, by arbitrary, I mean the limit is really how high the simulation goes. And of course, simulation has a limit at some point. And there, the basic idea is that we have a base network where we essentially make the first initial prediction from the dark matter to the gas. And then we have a refinement network that allows us to refine the gas levels kind of step by step. And then again, you can essentially specify as an input parameter how high you want the resolution to be. Yeah. So with this kind of approach, we can essentially go arbitrary high, but in the original EMBER-1, we have a fixed resolution that was given by essentially the size of the input neurons for our CNN.
Okay, with that, thank you. And I would like to thank Robert for this very nice talk. So you can stop here. And let's thank all the speakers for this session. So thank you. And I'll leave it up to Shazreen if she has any announcements to make before we end the session.
I'll make the announcement again later, but we'll be in touch regarding proceedings. We've contacted the invited speakers about the proceedings. We have a very limited number of pages, and so we're trying to figure out how best to incorporate everybody's contributions. We particularly would like to figure out a way to highlight the posters. So we'll be in touch. So keep an eye out on your email. There'll be a quick deadline, so keep an eye out on your email for that. But I'll announce it again also a little bit later. Thank you, everybody, and apologies for the disruption.
Apologies for the disruption. Thank you.
1, 2, Ladies and gentlemen, 1, 2, 3, 4, 5. Wana ni Zoom. Wana ngana watinda. Okay, sila. 1, 2. Weza kuna. 1, 2, 1, 2, 1, 2, 1, 2. Oh, okay. Zela zena tia room. Loba. 1, 2.
Is that open? 1, 2. Still looping. Let me try it outside.
You want to? Yes.
1, 2. Hello, hello, hello. Kale now?
Ese Oyukanga.
Yes, I can hear you.
Ngapela Oyukanga.
It's still looping.
Ezaka kaji. Mazoka yo. G.
Yes.
Zongara boy, il faut qu'on restart encore.
Never, guys, we need to find out why it's looping all the time. I can't be using this step all the time. That's not a solution. We need to find out why it's doing that all the time.
I also doing that. V somba tangu batoliero. V somba tangu batoliero.
Yang we Samir au kumano nani? Siko kile premier que après aux autres de wapi.
D'accord, okay, what day? Hello. 1, 2. Testing 1, 2.
C'est normal. What is normal?
1, 2. Testing 1, 2. 1, 2. On your side.
Ça va.
1, 2. 1, 2.
Siko eza calme.
1, 2.
Mais tango tobandaki elupaki.
Après quelques secondes, et ça là, bah, loupé. So, quand on me let's wait. Même le
Okay, everybody. Welcome back to the next session of our focus meeting. We'll start by an invited talk by Anshu Dubey. So welcome. Please come to the stage. Okay. Thank you very much.
Okay, seems like at least this one is going without any hitch. So far, so good, right? So the work that I'm going to be talking about, I actually don't do astrophysics myself. I only write code that people can use to do astrophysics with. So my co-authors are Austin Harris and Bronson Messer from Oak Ridge National Lab. And I will say that any questions that come to your mind about the actual simulations themselves, please hold them. Give them to me, I will transfer them to Austin and Bronson, and I'll get you answers. I will answer any questions that arise about the code itself, all right? With that disclaimer, let me get started. So, the acknowledgements. And then I want to tell you a little bit about the ExaStar project. So the US government, Department of Energy, started a project called Exascale Computing Project, where they knew that they were going to have computers that were going to come online that were going to be extremely difficult for codes to be efficient on, because they were going to be, most of their computing power comes from the GPUs, and they're not your standard NVIDIA GPUs. Both the Exascale platforms in the US have GPUs that come in Frontier at Oak Ridge, they come from AMD. In Aurora at Argonne, they come from Intel. And as you know, or maybe you don't, but let me tell you then that it's not even that within NVIDIA you can use the same code from one generation of GPU to the next. They change. And so you have to keep adjusting your code. And here you have whole new flavors of code. That's AMD and Intel. And so the DOE decided to invest in actually getting the codes ready before the machines came on floor, so that when they came on floor, the codes would be ready to go. And so there were 26 application projects, and one of them was ExaStar. ExaStar project actually wants to understand the nuclear processes that give rise to higher order nuclei, higher mass nuclei. And so what they want to do is simulation of core collapse supernova, neutron star mergers, et cetera, et cetera. So the challenge, each of the projects in ECP had to have a challenge problem using which they could demonstrate that they would actually be able to use the machine. The ECP project wasn't about computing itself. It was about getting the codes ready for computing, so you didn't really run simulations. We haven't finished running our simulations yet. All that we've succeeded in doing is to show that our demonstration problem works, and that using the same code, we have obtained somewhat lower fidelity solutions elsewhere. So our challenge problem was a 3D simulation of the initial stages of evolution following collapse and ion core bounds of a core collapse supernova. And the physics modules that we needed to do this computation were self-gravity. So this was still done with Newtonian self-gravity. We needed a shock hydrodynamics. Nuclear reactions, in this particular case, the nuclear reactions were used using a code called XNet, which can have, I think there were of the order of 400 or so nuclear species in the Bern network. And then there's a neutrino transport, which is a two-moment discrete Galerkin implementation. And it was using something of the order of 400 state variables, 500 state variables to run. So as you can see, it's a massive simulation size with a huge memory footprint. So also as a part of our meeting our so-called required goals was validation of the tornado neutrino transport model, the hydrodynamics module, and we do have a general relativistic MHD space-time solver, even though that wasn't exercised in the target problem, in the challenge problem, but it is available in the code now, and that is being used in the simulations. So these, again, disclaimer applies. I don't know the details of these, but these are pictures from the validation of various physics modules that were done. So they were done with streaming sine wave, Gaussian diffusion, etc. I know a little bit more about the spark hydrodynamics code. So in this, what was used was a relativistic shock tube. And even though and this is what shows you that this validation is absolutely fabulous, because you can't see the solid black lines. They're just so completely overlapping with the lines obtained with the simulation. So obviously this is working right. And then there is the validation of the general relativistic space-time solver. So you have relativistic density, pressure, magnetic pressure, and the B field arrows shown in the validation parts of the code. So now and of course, Frontier, the machine on which the challenge problem was run, it has shown to have overall performance of 1.1 exaflops. It has 74 Cray supercomputing cabinets. Each node contains more than 9,400 CPUs and more than 37,000 GPUs, because each core supports 6 GPUs. And so by and large, and there is the slingshot for connectivity. So one of the not so desirable artifacts of the work that was done during the Exascale project is that because all of the compute powers of the machine is concentrated in the GPUs, what vast majority of applications did was they said, we're going to just go park our data all on GPUs and just sit there and not move from there at all. And so and think about it, we started working on the ExaStar project in 2016, and the codes were ready. All of the codes took about up until 2022, 2023 timeframe to become ready for ExaStar. And so if the next stage of machines turns out to be significantly different from what we have this time around, again, the codes will have to undergo that same degree of maybe not the same degree, but at least a significant fraction of similar kind of refactoring in order to be able to utilize those machines. And I like to say that ExaStar, the code that is used by ExaStar is FlashX. The challenge problem run on Frontier. So what this is showing you is that this is the initial conditions, and this is the final stage. As you can see, the simulation hasn't evolved a whole lot more, but it ran correctly. It met all of the requirement criterions for things that needed to. It was certified by a certified astrophysics expert as being correct, as being valid, right? And the same simulation, actually, at the end of the talk, during the question and answer session, I'll run a movie of this very same simulation that was done on the predecessor of Frontier, that was Summit, but with lower fidelity. So I'll show you the movie of that. So going back to the code that was used in the simulations, FlashX, we decided that we were going to actually find a solution that is more future-proof than all of the other applications seem to be doing. So a little bit about FlashX. It was originally called Flash, and there is a version of Flash that still exists. It's largely used in high energy density physics now. But Flash was designed for a distributed memory parallel model, which means that you had a uniform kind of parallelization. You had a sequential version of the code. You did the computation sequentially. Then you did a bunch of communication with other processors in the machine, and then you continued with your computation. And so it was easy to abstract out the parallel operations from the arithmetic, the numerics of the code. But we were always using adaptive mesh refinement. And how many of you don't know what adaptive mesh refinement is? Okay, very few people. It's just that you're able to put a resolution only where you need. And so you don't have a uniform discretization, but it comes with its own complications in terms of additional bookkeeping that you need to do. And so as we saw that heterogeneous platforms were coming, we realized that we needed to adapt, and that some of the solvers could do with regeneration, needed modernization. So the capabilities that the currently open version. So now we've released the code under Apache 2.0 license, but you still have to get on the list of collaborators in order to access the code, and that's because we are required to keep track of everyone who's getting the code from us, and because we host on GitHub, that's the only mechanism by which we can keep track of who's getting the code. But otherwise, it's completely open source. It's Apache 2.0 license, which means that people can get it and use it in whichever way they want to use it. It has sorry, that's wrong. It's got that's correct, actually. It has two compressible hydrodynamic solvers. One of them is new, and it uses the GLM method for doing the MHD calculations. It has several nuclear networks, specialized equations of state, interface to Tornado, which can be imported as a module, so it's not a part of the code itself. It also has incompressible hydrodynamics and multi-phase flows with level sets. Multi-phase flows can also be used with compressible hydrodynamics because level set, the way in which the code is designed is it's composable, so you can permute and combine various units in ways that you want to configure, and there is a great deal of customizability in there. We also have two flavors of AMR, which is Paramesh and AMRX. We also support a fully uniform grid, and there is the performance portability layer, ORCA, with an embedded testing framework. And it's this performance portability layer, ORCA, that I'm going to be talking about, because I think what we have done with this code is something that at least I am not aware of any other code having done their performance portability and preparation for future in quite the same way. So what we realized was that what we needed to have orthogonal axes of optimization, because there are orthogonal axes of challenges. So the first thing to do is separate out arithmetic from control flow. Now, there are several solutions that are already out there in terms of, you write your code once and you can use it on multiple platforms. The most popularly known are Cocos and Raja, which make use of C++ template metaprogramming in order to let you have the unified code. But if you've got a code that has been around for a while and it's written in other languages, you're out of luck because you can't use them. But essentially, what those methods are libraries of data structures. They're not much more than that. So what you're doing is you're saying that I am not dictating what my data structure looks like. I'm letting you have that control, but I'll write my arithmetic, and you then bind the data structure of that arithmetic in a way that you can do with the data movement, etc. We do that with macros. And so the way we allow that to happen is that we allow macros to have multiple alternative definitions, including a null definition. And then we have a tool that can arbitrate on which definition to use where. So in that sense, it actually mimics the functionality of template metaprogramming without having to resort to C++. So to tell you a little bit about how that works is that what you have there is a macro definition for calculation of fluxes. All the names that are the names that are preceded with @m sign are actually the macro invocation. So loop begin is a macro, indices is a macro, loop end is a macro. And here are the alternative definitions of the macro. So the first set of definitions would let you operate doing the same arithmetic on one spatial point at a time, whereas the lower set of macros let you do the same arithmetic for all the spatial dimensions at a time. You could also have another set of definitions that would let you do on 1D or 2D spatial definitions. And so the point, though, is that the more error-prone part of the code, where you can introduce bugs if you're replicating and you're doing cut and paste, is the arithmetic, and you're writing only once. So again, you're binding your data structures to the actual arithmetic later on when you actually expand the macros. So this code can be invoked, and macros have recursion and they allow arguments also. So you can have this code section can be invoked by just saying hydroflux set and providing the names of the arrays on which you want to operate, and the arrays are defined elsewhere in whichever way you want them to be defined. There is an alternative way, and this is just to showcase the flexibility of the method, is that you could also remove the function altogether and replace that with a macro completely. And so what that tells you is that it's possible to have you can turn any arbitrary piece of code into a building block at your own discretion, which means that you have a great deal of flexibility in how you design your code. The second part is to be able to express algorithmic variants. By algorithmic variants, I mean is that the control flow, the order in which they do operation is different, even though the arithmetic is same. So now we've abstracted out the arithmetic using macros. Now what we want to do is we want to be able to actually say that I want to do the calculation in different ways. So FlashX, for example, supports 2 block structured AMR grid backends. One of them, and with AMR, you have to do a reconciliation of fluxes at fine coarse boundary in order to maintain your conservation laws. And the 2 AMR packages we have in FlashX do that differently. AMRX likes to do it on 1 refinement level at a time, whereas Paramesh likes to do all of the levels all at once. The second variant comes from the fact that if you're using a higher order method for integration, and because our abstraction is a block surrounded by its halo of ghost cells, you have to do a full communication intensive guard cell fill at every stage of the calculation, or else you can get a thicker set of guard cells, compute the inner layers of guard cells as a redundant calculation, but avoid having to do the guard cell fill n times, where n is the number of stages. So that's what is typically called the communication avoidance method. Turns out it's not obvious that one is always better than the other. On the CPU-only machines like Fugaku in Japan, actually, the communication avoidance is more expensive because the computation that happens in shock hydrodynamics is very arithmetic intensive. So therefore, we have these 4 variations that we need to be able to maintain, and COCOS and Raja and all of the other tools that you know of cannot do this. This is just not supported by them. We do this with a couple of tools called CGKit and Meloha. CGKit is a code generation toolkit. In this, you write your recipe for control flow in Python. And Meloha is a runtime tool that knows a few things. It knows how to move data from a host to a device. If you need to have n copies of, so for example, our blocks are very small. If you send 1 block at a time to the GPU, the cost of moving the data just completely outweighs any benefit you might get from the CPU. So what you want to do is you want to send a bunch of blocks. We typically find 40 to 80 blocks in 3D is the minimum that you need to send in order to amortize the cost of actual data transfer. And so Meloha knows how to flatten this data and how to make, if there are a scratch space needed on a per block basis, it knows to make n copies of that scratch space, et cetera, et cetera. And so CGKit has then templates for various variants, and then it writes the recipes in Python, and it expresses where to compute what. Like this piece of physics I want to do on CPU, this piece of physics I want to do on the GPU, I want the data to return back from GPU to CPU for this piece of physics, et cetera, et cetera. And from this recipe and this templates and the knowledge of where what is being mapped, it does the code generation for things like the time stepper, or for that matter, orchestration of any of the code at the highest level in any of the physics units. So code is basically internally decorated with directives, and all of that comes in the form of comments. So this is what a typical recipe in CGKit might look like. This is not the exact syntax, it's considerably simplified to explain, but here what's happening is you're saying that so AS depends upon AR, and so here the dependencies are expressed that translate into this graph And this graph is then optimized to fuse functions so that you're not moving back and forth. And at the bottom of it is specified where each of the actions needs to be computed. And then with Miloha, what we can do is basically we have these thread team configurations which we can make arbitrarily complex by daisy chaining them. And so, and then once we tell it, there are thread teams that then take over the job of moving data and launching the computation at the destination as required. So I know it's a lot to take in, which is why I'm sticking to the most high-level details, but I'll be happy to talk to anyone about it later as if people are more interested in finding out. Then we need 2 classes of code generators because the code itself cannot exist statically because every instance of an application, your data packets that you need to move are going to be different. Your control sequence is going to be different. So we have 2 classes of data packets. One class that collect data to be put into the data packets and generate code that will flatten into the data packets. And then there is the task function generator that consolidates functions to be invoked at the destination device and then unpack the data packets and give the device pointers to the code in order for it to be computed correctly. I'm not going to go into examples because we don't have details, but I can again show it to people who are interested in it. So here is the example of what our hydro variants are looking like. If you will notice here, the stage loop begins, and then the first thing you do a guard cell fill, and then inside of the inside loop you have a block initialization and intra-stage calculation, whereas in this instance, which is the communication avoidance one, you have the fill guard cell happening only once, but you have the block initialization and hydrodynamics loop has been shortened, so it's short-circuited. The important thing to notice is that the colored sections remain exactly the same, irrespective of which control flow one is running with. So this is the entire pipeline for the code generation that happens in the code, is that we have these templates and we have the recipe using which a control flow graph is created. The control flow graph then generates source code for the time stepper, and also from control flow graph, these JSON descriptions of the task come out. So all of this is human inspectable and human modifiable also. So you get these JSON generators that Miloha then can read and have its own data packet generator work. And so then we get the generated source code for data packet and task functions. The static source code is where the numerics actually sits, and that is then fed into the macroprocessor, and then fully assembled code is also applied, also gets macroprocessor applied to it, and in the end, all of the code is generated in a compilable language. And so then you can just apply your C or your Fortran or your C++ compiler, though we've exercised all of this largely only with C++ in some instance and Fortran in other instances. Then you get a platform executable, platform-specific executable. So in this instance, what the physicists actually code, physicists, once it is done, they don't need to know anything about this except for writing their recipe for control flow when they're ready to know how to assemble their application. So that's what, otherwise, the static code they write is the numerics and macros, and what is expected from them in their writing of these numerical code is enumeration of all data to be managed in the form of comments in the interface, because Miloha has to know, and then all allocations are registered with the tools. All data either transferred as argument or be block invariant. And that's really all they need to do, and then like I said, when they're ready to do their simulations, they have to write their recipe in Python, in a restricted Python. It isn't any arbitrary functionality that can be used in Python. No, it is just restricted Python, but the recipes are written in Python. And so this is the performance that we get from this code, is as you can see here on Fugaku, the non-communication avoidance version continues to work well until we get to 512 nodes, when the communication actually becomes more expensive than computation. But on GPU, the version where we are doing communication avoidance is always better. And the second thing is, if we were to not use Miloha and just simply use OpenACC one block at a time, then this would be the performance. But using Miloha and being able to consolidate the blocks and also to be able to do some latency hiding by using asynchronous data transfer, we get this level of performance. Porting to a new platform, in an ideal world, all that we should need to do for a new platform is to add to the library of recipe templates and build up runtime pipelines for Miloha use. In real world, it doesn't quite work out that way, so we need to add variants for solvers with alternative definitions of macros, and sometimes you just need a new algorithm, though the one algorithm will simply not work. And with that, the movie from the simulations. And why is this not starting? Okay, and I'm happy to take questions while the movie is running.
Thank you very much for the very impressive overview of ExaStar. Are there any questions? Yes.
Thank you for a very nice talk. And actually, I have two questions. One is, so yeah, we usually use many libraries. How the system, so you use libraries.
That's always been a problem. For example, in our case also, if we have any diffusion, we need to use Hyper, which is a library. And so getting the interoperability between threads can be a challenge. Now, under the ECP project, one initiative that started is called E4S. And what E4S initiative is doing is it's making the libraries compatible with one another. And so once you're aware of how those libraries need to work together with one another, you can, first of all, you can use them and you can repurpose the code to interact with them. So in our case, for example, the way this would work is when we are creating our control flow, the recipe, what we would say is we would make any access to the library as a so-called GPU operation at our interface level so that the library can do what it needs to with any of the devices it wants to.
Okay, thank you. Another quick question would be, so the system can automatically hide communication, or overlap communication and calculation.
It is. That's what we are
That's great.
trying to make happen.
Thank you for a very nice talk. I want to understand the performance which you demonstrated over here. Does it also account for the I/O, which is essentially in the input-output?
No.
And then if that's the case, how well whole this infrastructure is accustomed to natural I/O processing?
I did not include it, but there is an asynchronous I/O built in, which means that the only noticeable time that you have to account for in the running of the simulation is for data to move to the I/O node. And after that, it is asynchronously sending data to the disk while overlapping with the actual computation. So it does work very well. I just haven't included that part in this talk because that's not a part of orchestration system.
Any other questions?
This might be a physics question. You showed us the initial conditions and then the final stage, but they were very close. But the processes in stellar explosions are highly nonlinear, so why would that convince me that you verified the physics?
So that's individual validations, of course, happened, right? And also, so this is the movies that I have shown are essentially the same simulation run with the lower resolution and fewer species in the nuclear network and fewer group elements in Tornado. And so, and that's as far as we can go, right? And that's, but because basically what it's telling us is that the various parts of physics that need to interoperate with one another are operating correctly. And I'm not going to claim that that means that the simulations we run is not going to have problems. It will. That's been my experience. It will. But we are as ready as we can be to do this.
Okay, thank you very much. And I think with that, let's thank Anshu again. Very nice talk. And then next up, we have Federica Bianco.
Hello.
Do I wait for them? Okay. Yes, thank you. You can do it without the slides. It'll be less entertaining though.
Technical difficulties.
Yeah, that's me. All right, so my name is Federica Bianco. I'm at the University of Delaware. I'm also at Rubin Observatory. And I'm going to talk to you about some of the portfolio of research of a bunch of my students, which is on light echoes, which I think are fascinating from an AI perspective because, as I will show you, they're rare, faint, time-evolving, they're morphologically diverse. We do need AI to detect them and characterize them, but they're a really bad target for AI. So my plan was to verify how far can we push AI to do this. So the true heroes of the story, of the part of the story that I'm going to tell, are Dr. Xiaolong Li. He's the first of my graduate students to get a PhD. And he's now a Catalyst Fellow at Johns Hopkins University. And Rodiat Ayinde, who's a Nigerian student at Lincoln University. Lincoln University is a historically Black college and university near Delaware. And she graduated from computer science there and is doing internship work with me. And we have 2 NSF grants and 1 paper out. So a lot of technical stuff I'll probably skip because you can read the paper. But let me tell you what are light echoes first. I think they're one of the most fascinating astrophysical objects, in my opinion. So they relate to time domain astronomy, which is the broad scope of my research, the intersection of AI and time domain astronomy. So they're time evolving phenomena. So here we have the Earth and we have a stellar explosion. And what we normally do with this, might be a supernova. We get photons from the supernova. If we're lucky enough, we're pointing the telescope in the right direction at the right time, and we see the supernova, and it would look something like this. We have a template of the sky. That's how the sky normally looks. And then we have a night image, we call the search image, where we have that tiny little blob on the top, on the bottom left of the galaxy. And it's very hard to tell that there is something different in this image, but we subtract them, we do difference imaging, we're left with a point source. That's our detection, that's the typical time domain, bread and butter of time domain astronomy. Rubin Observatory will deliver 10 million of those every night, but light echoes are different. So imagine that we have the same stellar explosion, but there is some dust in space between us and the supernova, or around the supernova, as I've drawn it in this case. And dust here is just molecules that have reflective properties. So now we still may see the supernova directly, but then some light that goes in a different direction from Earth may reflect on the dust and then be bounced back to Earth. So we would see the supernova this way as well, but we would see it later because the travel path of light is longer. Also, we would see different positions, different timelines of the supernova reflected by different positions on the dust. And we would end up seeing something like this. This is a light echo. This is a poster child for light echo. Most light echoes are not that pretty. This is 1987A. And you see those beautiful 2 rings. This is because the dust is in front of the supernova, so between us and the supernova. It would look circular also if the dust was surrounding the supernova. But in most cases, we're not that lucky. And the light echoes that I'm really interested in are those that are reflected serendipitously by historical transients. So a supernova goes off, Tycho, Casey, and then
Centuries later, the light comes back to us, reflected by a tiny little patch of dust somewhere in the sky. And it might look like that. That's another poster child. That's a beautiful light echo on the elephant trunk. This is the Carina Nebula, and the transient is Eta Car, a very long 30-year transient. I'm going to point out some things here. You see the black and white structure. That's the signature of time domain astronomy. This is a difference image. So the stuff that is black is an old light echo. Light was there earlier in the image that has been subtracted. And then the new stuff, the dust that is getting illuminated more recently, is bright. So we do have this black and white structure. Something like that is easy to detect in an image. But most likely, I will look for something like this. Still not that bad. Something like this. And the points that I want to make, they can look much worse even. And the point that I want to make is that these transients are faint. They're really at the limit of signal-to-noise ratio. In fact, they go all the way down into the noise. We only detect the ones that are above the noise, but light echoes are everywhere. They're time evolving, so we can stack images to get really, really deep stack to detect them. And they're morphologically diverse, and cherry on top, they're also really rare. We have like order of 100 examples of those all together, of light echoes that are detected serendipitously this way. But I want to detect them, and I want to detect them with Rubin. So I'm going to argue that Rubin LSST is the perfect light echo survey, because it covers the fact that they're rare by, conversion to PPT always gives me troubles. It covers the fact that they're rare because it's a very wide area survey. It covers 20,000 square degrees of southern sky at 0.2 arc seconds per pixel, so highly resolved, so we can see them in all their structure, and we can see the diverse morphology at that resolution. Covers the fact that they're faint because it's a deep survey. It goes down to magnitude 24 in R with a single image, can go down to greater than 26 in stacks. And it's a time domain survey in its essence, so we can see them, and the time scales that we cover are hours to decades, so they're really good for any kind of light echoes, the ones that reflect short events and the ones that reflect decades-long events like Eta Carinae. Fine. But we have 1,000 3.2 gigapixel images per night, and the current state of the art for detecting light echoes is to give them to one expert, really just mostly one person. His name is Armin Rest. He's been doing light echoes for 30 years. And ask him, Armin, do you see a light echo in my image? And we can't do it for this number of images, not even with Armin. In fact, even if you take all of the population in the world and you scale from Galaxy Zoo numbers, there's not enough people to do this. Okay, so we do need AI. But the things that I said should make it clear that this is a challenging problem. Morphologically diverse signal at the limit of signal-to-noise ratio, and rare, which means very few training examples. Thankfully, Dr. Zhao Longling is kind of a magician, and so he worked on the first iteration of this work, which is how do we detect them in images? We use Atlas images. It's a time domain survey in a single band, so Rubin is a little bit different, but bear with me. So we wanted to see, computer vision people would tell you like detection of objects is it's a solved problem. And I wanted to see, is it really solved if my objects are so different from what you have really designed your models for? So we started with state-of-the-art at the time, computer vision models. YOLO, you only look once, which is a localization model that uses convolutional, it's a convolutional neural network at its essence, that identifies and localizes objects. The first problem was the rarity of the event, so we actually worked with 17 images with light echoes in them, so maybe 30 examples. We did augmentation, and I will point out just a few of the decisions that we made. We had to fight with the referee a bit on this one. I did not want to do regular augmentation that people do in images of real-world stuff, because I didn't want to mess with the noise. The noise characteristic of an astrophysical image are very peculiar, and injecting the wrong noise just to do augmentation was actually detrimental. So we only did geometric augmentations and rotations and reflections and stuff. The second problem that we typically have with astrophysical images is that our objects are not objects. At best, they're balls of gas and fire. In the case of light echoes, it's a reflection on a diffuse medium. It doesn't have edges. There's a million ways in which I can label these objects. They're all valid. I cannot tell you what is one light echo, what is a light echo complex. So that has to do with how do we then define and evaluate the models. What we end up with is replacing what is typically used in computer vision problem, which is the intersection over the union. So the intersection of what the prediction is and what the label is, the human bounding box, with the intersection over the prediction. So that if my model has labeled light echoes more finely than my human labeler, then we still get a positive result. I'm going to skip through a bunch of stuff in the interest of time. We did a bunch of fun things with the loss function, including modifying the IAU with IOP, but only for light echoes, not for stars or asteroids. We had a focal loss in the piece that deals with the confidence of the classification, et cetera, et cetera, et cetera. And the punchline is that with only 17 examples, starting with 17 images with light echoes, we obtain a recall of 70% at a precision of 95. This is a really remarkable result that took a lot of really hard work from Xiaolong. And then we revisited all of the light echo images from Atlas, and what had we missed? We'd missed some major stuff, because when you have human labelers, you do miss stuff, even if you put 3 people on the same images. And we've missed some more exotic and tiny things that were eluding the human eye. We even found some light echoes that don't have the black counterpart that are entirely new. So this is an emerging light echo that my model figured out, Xiaolong's model figured out how to detect, even though we didn't have things like that in the training set. And then the other thing we wanted to do is segment them. So once we have them, what is really the morphology of the light echo? And another solved problem, segmentation, so solved that they call the most recent model, which is a vision transformer, segment anything. This is a model from Meta AI, and we wanted to see, can it really segment anything? So Rodiat worked on this, and we started from just very basic. Let's just give it the light echoes and see if it really can segment anything. And of course it can't, but we had no hope that it would. Of course, this was a lost cause from the start. But Sam works with prompt. You can give him more information about the images. In real world, typically this is like a caption. For us, it's not going to be a caption. I can tell it is a light echo. That won't help. But you can give it a couple of different prompts. One of them is you can give it points. You can say some of the pixels are in the light echo, some of the pixels are out. Can you figure out what's the edge? I had fairly high hopes on this one, and it did not go well. There's multiple masks that Sam produces for every iteration that you do. They went from really sparse, didn't find the light echo, to the whole image is a light echo. And then we did another prompt, which is a binding box. So we used the binding boxes that we had from our previous model, and we passed those as well as to help the model identify the light echoes. And that really worked. I was surprised that it worked so well. What you see in the center is a binary mask, but really the output is a probabilistic mask. So that actually might tell me about the structure of the light echo in a more fine form. And we found it for that example, which was easy. For examples that are harder, there's a really bright star there. So it's remarkable that it finds the edges of the light echoes here, faint light echoes, et cetera, et cetera. As an added bonus, we're also applying the things that we've learned from light echoes to other known real-world images. These are actually real-world images. They're geography projects that I work on with colleagues at the University of Delaware. One of them is also NSF funded. We're looking to segment and identify rare earth mineral mines. I want to flag that a lot of those mines are actually in Africa. So we have targets in South Africa and Zimbabwe. Those are on the maps. And they're some of our most active regions. And on food sustainability projects in Nigeria, which is why Rodia is also involved on this. We're trying to identify and count fish ponds for fish ecology and food sustainability. And we're also doing generative AI to augment the data set, but I don't have time to tell you about it.
Very much. Are there any questions from the audience? Oh, yes, I see many.
Thanks for the great talk, Fed. This is very cool. Something, I think I never really thought much about transients that weren't going to be basically point-like. So what about with the alert stream, how we're going to get stamps as part of the alert stream?
Yeah.
are there going to be any issues? Are the stamps going to be big enough that you'll be able to reliably run your classifier on those as the alerts come out? Or do we need to be thinking a little bit about those, how we do those stamps?
Yeah, for the light echoes, I actually don't think we're likely to get a lot of the alerts, because even the ones that I've showed you are really high signal to noise ratio. So many of them will be fainter. So I imagine that I will need to find resources to run the models on the images themselves or on different images. Some of them will show, but yes, the stamps might not be big enough. Another interesting case of an extended transient, though, that I think is a little bit more hopeful for the alert stream is comets. Comets have tails, but they also have a core, and our pipelines are going to be optimized for point sources. So that's what we expect to find.
Okay, another quick question.
Good to see you, by the way.
Hi, Federica.
Hello.
Thanks. Great talk. I love the sum model, how you're using it. I'm not sure you know, but a couple of days ago, there was the SUM2 release.
I saw that.
So I was wondering, these are sequences of images, right?
Yeah.
So can you apply SUM2 to this?
Yeah. So we, in fact, we want to use the sequences of images both for the detection and for the segmentation. And so it was kind of like separated from SAM2, but also, yeah, related to SAM2. Like this is true for all the models. There's a lot of information that we haven't even used yet. The evolution as well as the colors. We've done it in a single color, but light echoes do have characteristics colors. So, and also SAM2, yes, came out at the wrong time because now I had to answer questions on SAM2 and I'm not prepared.
Let's thank Federica again. Okay. Yes, if we can switch, then our next speaker will be Guillermo Cabrera. Please come up to the stage. You will have half an hour as well, so I'll give you a 5-minute warning when you're at 20 minutes.
All right. Hello, everyone. Thank you for inviting me. It's a pleasure to be here. I'm here on behalf of the Alerce broker. This is one of the 7 brokers, of the official brokers for the LSST. And today I want to talk a bit about how machine learning is implemented in Alerce and what are the challenges regarding the implementation of these models in practice. So about today's story, this is what we're going to talk about. So first, I'm going to give a brief introduction on what alert brokers are. Then I'm going to talk about Alerce. After that, I'm going to talk a bit about machine learning, then about machine learning in the real world, which is not the same as in simulations, and then lessons learned and lessons to be learned. And spoiler alert, at some point you'll see these 2 guys in the presentation, and we'll talk about them later. So, alert streams. So thanks, Federica. She talked about this, so I'm going to briefly go over it. Basically, Rubin, or any survey telescope that's considering time, it's going to be it's going to be serving the sky, right? So we're going to have a lot of these images. And usually what we will do is that we will have a template image, which is like a historical image from the past. And then we will have the science image, which would be the image from last night. And then what we will do is that, I mean, not me, Rubin is going to do this, right? They're going to subtract them, and if something appears in the difference image, then they're going to emit an alert, okay? So whenever something changes, an alert is going to be emitted. And if you think about this, you can have an alert emitted tonight for a particular point in the sky, and then you can have another alert emitted in maybe 2 or 3 days, and then another alert emitted in 6 more days, and so on and so forth. And then what we can do with this is, so we'll have these image stamps, right? And from the image stamps, we can calculate what's called the light curve. So in this plot, I'm showing the time on the x-axis and the brightness on the y-axis. And you can, for the first alert, this one, I can calculate the flux on the difference image, and I'm going to get a point here. And then for the next alert, I'm going to do the same thing, and the same thing for the next one, and so on and so forth. And this is what we call a light curve, all right? And so this is how they look right now on Alerce, the light curves. And you can see that we have different bands. We have also the uncertainties on the estimations of the magnitude in this case. And we also have here non-detection. So that means that at those times, the source was not detected as an alert. Okay? And right now, we're working with CDF, which is one of the precursors for the Vera Rubin. And right now, Alerce is working, and we're ingesting every night between 0.1 to 1 million alerts per night. Okay, but this is going to scale up in maybe less than a year to 10 million alerts per night when the Rubin starts operating. So this is a huge challenge, right? I mean, it's a lot of data, 10 million of this, and we need to do something about those. So that's where the brokers come. So the brokers, so I'm going to talk first about Alerce. Alerce is one of the brokers. It's the one led by the Chilean community, and it's a tree. I'm not sure if you knew this, but I noticed on the day of the hackathon that not everyone knew that Alerce was a tree. So Alerce is a tree, and it may be the oldest, the oldest tree in the world may be an Alerce. So this is a press release about one tree, all right? And it's a tree that it grows in South America, particularly in Chile and in Argentina. So how do we think that the future of time domain will be? Well, we're going to have the survey telescopes, and the survey telescopes are going to start emitting alerts. Those alerts are going to be received by the community brokers, and the community brokers are going to process this, are going to aggregate some data to the alert stream, and then they're going to emit it. And this is going to be emitted to downstream brokers and TOMs, but also directly to follow-up resources or to the community. And most likely what's going to happen is that once the user community start getting these alerts and they start finding cool stuff, they're going to want to go back and see what's happening on the catalogs, or if I can do some additional follow-ups on some particular sources and stuff like that, right? So the products that the brokers are offering, or we're saying that we're going to do, I mean, most of these we already do, but are related to Kafka streams, cross-match, access to the databases and the APIs, access to the data in general, filtering. So when you get an alert from that passes a particular filter, then you need to have a notification of that. A lot of classification, calculating different features, watch lists. So that's basically you want to see in a position in the sky if something changes, and then you get a notification. Well, that's the things we do. Follow-up, multi-messenger, multi-stream, detection of outliers and anomalies. We do that too. We have models for that. Data releases, and of course, super important, being able to reproduce everything that we achieve. So the Vera Rubin made a call for community brokers in 2019. Then there was a call for full proposals in 2020, and the selection was made in 2021. And there were 7 community brokers that were selected that are going to receive the full LSST stream. And those are the ones that are shown here. There are 3 in the United States, there are 3 in Europe, and Alerce in Chile. And they also selected 2 downstream brokers. So if you want to get access to the alerts from Rubin, then what you need to do is connect to one of the brokers. The Rubin is not going to send the full stream, the full alert stream to everyone in the world, okay? You have to connect through one of them. And something that's super important is that we have to create the services for you to connect to our alert stream. Okay, so if you wanted to, we can send you the 10 million alerts per night, okay? Scientific questions. So the Alerce project has a scientific board. Amelia here is part of the scientific board. And it's 10 people from different expertise, scientists. And we have people or scientists from that work on transients, on active galactic nuclei, on variable stars. We don't have anyone on solar systems, so that's usually like something we just don't do because we don't have the people, right? But if anyone is interested in working on alerts that are related to the solar system, we would be super happy to have you on board. And we also have in the scientific board people that work on machine learning and on statistics. So it's quite broad. And this is super important because Alerce, it's a broad community broker. So we're talking about different use cases. The tools we've developed, okay? So we have the Supernova Hunter. This is currently working. Most likely the video is not going to work, so I'm going to try this, but it didn't work. So I'm going back, and I'm going to tell you what the video was supposed to be doing, all right? So basically, the Supernova Hunter is a system that reports every night, as soon as we get the alert, it reports whether one of the alerts is either a supernova or not. Okay, so how do we do this? I'm going to explain it a bit later. But with only one alert, we're able to detect if a supernova, if an alert is a supernova or not. So there's a list over here of potential candidates from last night, and you can access the data, and you can also go into the data and try to figure out if this is real or not. There are people inside Alerce that every night report to TSN, the TNS, the supernovas that appear every night. So every morning, someone connects to the system and says, oh, yes, this is supernova. Oh, this is not. And we have a communication system inside Alerce in which the scientists can talk and discuss about each of these potential supernova candidates. This is another video that's not going to play. I hope I get an image. I got an image. Great. All right, so we also have the Supernova Hunt, this is the Explorer, the Alerce Explorer. And in this case, you can explore everything related to light curves. So you can see here the light curve, and you have access to the image stamps, you have access to Pan-STARRS images, but you can also do cross-matching with other catalogs. That was supposed to be shown in the video somewhere around here. You can cross-match with other catalogs. You have different classifiers that classify the light curve. And you have the probability of being one of many classes. And in the future, hopefully not longer than a month from now, we'll have the anomaly detection model in production. And I'm going to talk about that in a bit. So models, what models do we have? So you know that deep learning has become a trend in astronomy. Most likely you all heard about what deep learning is. Have you heard about deep learning? Can you raise your hands if you heard about deep learning? Okay, great. Can you raise your hands if you trained a deep learning model? Oh, great. So there's a lot of people that, oh, maybe this is going to be too basics then. So basically this is the number of papers that says deep learning in one of these journals in time. And you can see that there was around 2016-ish. There was a blow up on the number of papers that were using deep learning. And it kind of feels like it's getting to a plateau, but I'm not really sure because we don't have the data, the complete data for 2024, because we haven't finished 2024. And so yeah, so it seems like deep learning is really promising, like everyone is using it. We've heard really great talks about this during this conference. And what is deep learning? So deep learning is basically, it starts with a neuron, and what you want to do is, if you have one neuron and you connect a lot of them, you can have like a neural system or a neural network. And deep learning is today mostly about modeling mathematically a neuron, and then connecting a lot of them, and then you have like an artificial neural network, and that's it, okay? So to me, deep learning is the same as playing with Legos. Do you know Legos? Raise your hands if you know what Legos are. Okay, great. I think more people knew about deep learning than Legos. So it's like playing with Legos, right? You have a bunch of Lego pieces and you can create something super cool, right? And immediately you understand what this is, right? With a few number of pieces, there's a representation of that, and you know exactly what it is, right? And you can have more Legos, sorry, and you can have a larger, more complex thing. But if you think about it, the representation, it's not based directly on the number of Legos, right? It's related on how you put them together, okay? So to me, deep learning is exactly the same. It's like playing with Legos. I love Legos. I have a bunch of them at home. And basically, you start with a neuron, right? And that's the basic Lego unit. And if you connect a bunch of them, you can do some particular task. And if you connect a whole bunch of them, you can have like a really complex neural network. And it's all about the ingenuity on how to connect the pieces. It's all about thinking how to connect them, how to train them, about thinking about the loss function, how you optimize the weights of the neuron and stuff like that. So the supernova hunter that I showed before, I showed it, but the video didn't play. Basically has a has a convolutional neural networks behind the scenes, and this is basically one type of artificial neural network that is super common. This was developed in 2021. Well, actually, it was developed in 2020, but the paper got published in 2021. And what it does is it grabs three images, the template, the science image, and the difference image, and it performs some rotational invariance operations, and then it classifies this into AGN, supernova, variable star, asteroid, or bogus, okay? Another example of a neural network that we currently work, oh, and by the way, these are Rodrigo and Esteban, who were the guys who did this, all right? Another thing that we have already working, it's Delight. This was developed by Francisco Forster, sorry. And what it does is that you grab the image from pan-stars, and then you try to figure out exactly, for a particular supernova or transient, exactly what the host galaxy was, okay? And the way he did it was he created this really smart multi-resolution neural network. So he based his idea on how the human eye works. So apparently we have a high resolution in the middle of our eye and in the center, and a lower resolution around the point that we're looking at. And so he did exactly that, and he created this multi-resolution neural network. You can install it by doing pip install Astro Delight, and then you can directly use it. So, but now about the light curve classifier. How does the light curve classifier, how we classify light curves? Well, basically we have a really broad taxonomy, which is this one. This is a work that was performed by Paula Sanchez-Saez. And basically we get the light curves and we calculate a whole bunch of features from them, okay? And we calculate around 175 features, and then we put all that into a balanced hierarchical random forest. And then we can classify into all these types of features. I don't have enough time to go in detail, but this is basically our confusion matrix. And so then the question rises, like, if deep learning is so cool, why do we have a classic model in production? So did you notice that? So I showed two deep learning models, but the one for light curves, it's not a deep learning model, it's a random forest, which is like a really basic model, okay? And the answer is, so how many of you were in South Korea in 2022? Okay, great. So you might have already seen this plot. I showed it there, this table. So a lot of papers, as I showed before, came out with new deep learning architectures and new deep learning ways of doing light curve classification and stuff like that. And we said, oh, great, these are really great tools. So we tried them all. Not all, there are too many. But we tried a lot of them, okay? And what happened is that, if you see here, there's the random forest for different tasks, and in most of them, in all of them, the random forest would outperform the recurrent neural networks or the neural networks from that time, okay? The closest one that we got was Rapid, which was for classifying transients, and still it didn't perform as well as the random forest. So that's why we don't have a deep learning model in production, because actually they don't work with real data. So a lot of papers have been published with simulations or with particular data sets selected like very carefully. But when we think about a broker, we are receiving 10 million alerts, right? And we need to classify all those. So it's not like we can choose, we get to choose like these are gonna be the ones, I'm gonna grab the supernova and classify only the supernova, right? We have everything, and we need our models to work with everything, right? So this is how the machine learning development workflow works in ALERS, and I'm gonna explain you a bit about this because it's important. So usually we start with the research, right? So we say, what if we create this particular model? And usually this is done by students, all right? So a student would work on a particular machine learning model or a postdoc, and they will come up with a model that they will test on real data. So that's super important. Everything gets tested on real data. And what I mean by real data is like the whole stream. And then it goes into development. If we choose a model that we want to put into development, then it goes into development. And this usually takes between 1 and 6 months, depending on how good the code was from the student, all right? So if we want to put it in production, we first go to development, and this is done by Ignacio Reyes and his team. So he's the lead engineer on Alerce. And he looks kind of grumpy because usually when you get the models, he gets the model and he's like, oh man, really? Again? Okay, and so once they are developed and they are in what we call development stage, we put them into staging. So what does this mean? We have a replicate of the system, the whole system, that it's only to test that everything is okay. Okay, and this is not the system that you get access to. It's another one, like a replication of that system that we have internally. And when it's in staging, then it goes through quality assurance, okay? And this is Alejandra Muñoz, and she's the quality assurance manager, or the expert. And what she does is she performs a lot of tests on the real alert stream. So the model was trained usually with some particular training set, right? But then we put it in staging, and it receives the whole alert stream, right? And it starts classifying stuff. And she does stuff like plotting period magnitudes, diagrams, and see how it performs or what it is detecting or classifying in different zones of the sky and all that. And after that, after it passes that test, it goes into production, okay? And when it goes into production, then you can see it on any of our services, yeah? Okay. And this is kind of the workflow. So everything that's in production has been really well tested, okay? So if you get to Alerce, that has been tested thoroughly. Okay, spoiled. So, as I said before, no deep learning model has been put in production so far until this model over here, which is called ATAT, the Astronomical Transformer for Time Series and Tabular Data. Okay, and so this is the first model that has been able to get all the way up to staging. Okay, and I'm going to talk to you briefly about what it is. So raise your hands if you know what a transformer is. You all know what a transformer is, so I'm going to be really fast on this. So a transformer is basically it was created for text. Okay, so for natural language. And the idea was that if I have a sentence like this, we would create something that's called a self-attention mechanism. And basically, you go through a model, right, that is going to create a representation of each of these words. Okay, and that's basically a vector. You can think of a vector for each of these words. But what you want the representation to be is to have some context. Okay, so for example, if I want to understand what barked is, most likely, I'm going to have to, I would like to pay some attention to happy and to dog, okay? Because, so dog is important to understand what the representation for bark is. And this is done by using this, this attention. So this is like the percentage of attention that you have to pay to each of the words in the input. And the other thing that's super important here, and it's where I'm heading to, is that there is something called a position encoding, which basically encodes in a vector the position of the word. Okay, so for example, for the word D, we have I equal 1, so the position, you have a vector representing the position I equals 1, and so on and so forth. And all this goes into the multi-head self-attention blocks, which are the model, the transformer. For the light curves, we do something very similar, but now the position encoding, instead of encoding the position, what it does is encodes time, okay? So that means that for each observation, we input the flux. It gets a representation vector for the flux plus a representation vector for the time, and that goes into the multi-head self-attention blocks. All right? So This is AT-AT. This was a really smart idea by a former student, Nicolás Astorga, and it was implemented by Daniel Muñoz for Alerce. Daniel Moreno. Oh, man, he's gonna kill me. And the nice idea about this is that we have a transformer for light curves, but we also have a transformer for features. So it's, they combine in the middle and they create a representation that considers time and features at the same time, or tabular data in general. And so we trained this on the force photometry data. So this is new data that we started getting in October last year from CDF. And you can notice, so this is the random forest is on the left, AT-AT is on the right. AT-AT performs slightly better. And the other thing that you may notice, or maybe not, but we added new classes. So now our taxonomy is more complex, okay? And this is where these guys come into play. So the code name for this is Handsome Squidward, and the code name for this is Mbappé, okay? Why? No idea. The engineers decided to put that name to the models, okay? So right now we have in staging those two models. I was expecting to have them on production like 1 month ago, but to be honest, it has been really tough because there are different things that Alejandra has found that they doesn't work correctly. We also have on staging an outlier detection method. I can talk to you about that later in the coffee break or something. So right now, Alejandra is working hard on trying to make sure that Mbappé works correctly and that Handsome Squidward also works correctly, as soon as also with the outlier detection algorithm. Hopefully, we'll have them ready in a month or so. And so one of the things that Alejandra detected was this. So this is a light curve. So we have the time on the x-axis and the flux on the y-axis. Can you see that there's something weird there? So you know what these guys from CDF did to us? Basically, one day they decided to have a high cadence during one night or during a couple of nights. So our model was working correctly, and suddenly we got around 230 points on a very small amount of time. So that screws up all the models, right? So it was, for us, it was like, dude, why didn't you tell us, right? And we suddenly received all this, right? And so I don't have time to explain this in detail, but basically, Daniel and Alejandro started working on this, and they started figuring out the way of changing the models in order to do this. And we already knew that the change of cadence was a problem. And most likely this is going to be even a harder problem for Rubin. We published this paper in 2023 that addressed that problem through changing the positional coding. I can talk about this later. Okay, so lessons learned. A model trained on simulations will not evaluate the same in real data. It is not simple to put a model into production. Distribution shifts need to be taken into account, and changes in cadence deeply impact deep learning models. And some ideas, active learning, transient learning, and milling, sampling invariant models. Just 2 more slides, very quick. So, all right, sorry. So this is the Alerce team. So when I was preparing this talk, I would send them like WhatsApp, like saying, hey dude, I need this plot or whatever, and they sent me that back. So they are meeting right now in Santiago having beers. I'm not sure if right now, it's too early in Santiago to do that. And the other thing is an announcement. So we're holding up the Astroinformatics Conference in December from 9 to 13 in Puerto Natales. Puerto Natales is a really nice place. You have really nice hikes and stuff like that. So if you want to be part of it, you can go in there and register. That's it. Thank you, and sorry for being there.
Thank you very much. We have a little bit of time for some questions. Go there first.
Thank you, Guillermo. Fantastic talk. So I'm just amazed by the fact that the model for any algorithm only relying on tabular data actually works much better than the model with the multimodal. So can you comment on why it's happening? I mean, for your personal opinion?
So the classic model, why it works better than the deep learning model?
Yeah.
Okay, yeah. So basically because the features that we calculate, which are like 175, right? They are features that we designed. So we know that those features correlate with the labels that we're trying to predict. And on the other hand, the deep learning models, what they do is that they calculate automatically their features, right? And so that means that unless you put in those features into the models directly, which are like 175, they most likely are not going to work correctly.
I also forgot to ask, you actually got humongous number of features. Can you comment, what actually they are? Like, they are beyond actually just the photometry and the uncertainty of, photometry, right?
They're like, so we have very basic features, like, for example, I don't know, the average magnitude or the deviation of the magnitudes and stuff like that. But we also have some more complex features. So for example, we have autoregressive models. We also have like parametric models for supernova, and it's a whole lot of them.
Okay, yeah. Alerce is great. I'm a great fan of it. The transformer for the features, you said you have a transformer for the light curve and a transformer for the feature. How does the positional encoding work in that?
So in the case of the transformer for the features, it doesn't have a positional encoding. So the way it works is that you grab each value of a feature and you turn it into a vector, and then those vectors are concatenated, and then they go into the attention mechanism.
But if it's a transformer, doesn't it then predict on the bulk, like on the distribution of features and not on the features and their correlation?
I'm not sure I get that straight. So for example, if you have one feature for one particular object, then you're going to create a vector for that, right? And you'll have a lot of vectors for all these features. I mean, they're not implicitly into the transformer.
Okay, and any last quick burning questions? And then maybe in the meantime, we can already switch to the slides from Bernardo.
It's a very nice talk. My question is that if you look at the problem from the point of view of what are the interesting objects for me to follow up, then you need to make a decision quickly with the minimal time span between the first and the last. And I was just asking whether you care to comment on that.
Okay, so that's a very good question. So I think that's a problem. It's like an open problem right now. We don't know exactly how this is going to work, like if we want to immediately do the follow-up after this. We know how our models perform in terms of the number of alerts we get. So we usually do that. We make sure that everything that they start improving as you get more alerts and stuff like that. But usually when you have like 6 alerts, they're not very good. No model is very good with 6 alerts. And so it's, as I say, it's like an open problem. And actually Michelle, who just left, we've been talking about that a lot because we know that that's going to be a huge problem. And also it's going to be a huge problem for anomaly detection when you have 2 or 3 points and you need to do a rapid follow-up. How can you make sure that you're not going to get like anything?
Thank Guillermo again.
Thank you.
And then we're down to our last talk of this after lunch session by Bernardo Fraga. Please go ahead. I'll give you a 2-minute warning.
So, hello, everyone. Thanks the organizers for giving me this opportunity to be here. I come all the way from Brazil, from the Brazilian Center for Physics Research, or CBPF. This work is done together with other people from CBPF and from another Also from, okay, good now, thanks. Also from another broker for the LSST, which is Think. So thanks, Guillermo. You will save me a lot of time because you explained already what a broker is. So I can skip directly to Think. Now, Think is based on France, but it takes a slightly different approach from Alerce in that although the computing is centralized in Paris, the science development teams are scattered all over the world, and pretty much anyone can contribute to Think if they want to. It's been working as Alerce with the ZTF since 2019. And Think is completely open source, and it won last year a prize for open science given by the France's Ministry of Higher Education and Research. And the goal here is to present the classifiers that were either adapted from their work in ZTF or built specially to work with LSST data. And since LSST is not here, we already heard Guillermo say that, well, real data is different from simulations, but simulation is all we get for LSST right now. So the data set we work is, it's called Elastic, it's a simulated data set, obviously. It was part of a challenge called, well, I won't read this. It's about 50-something million of alerts, simulated time domain events on a bunch of classes. So the main goal for Elastic was to test the broker's infrastructure to ingest alerts and process them. But there was a secondary goal, which we took advantage of it, was to evaluate machine learning algorithms. And one thing that is important for me later is that this is the classification of the classes of Elastic. And you can see that those usual classes that we are used to, like different types of supernova, variable stars, they are grouped together in these 5 that I call broad classes: the supernova-like, fast, long, periodic, and non-periodic. So just a quick word for Elastic. There was a training sample that was given to all brokers in mid-2022, and then this was supposed to be the training sample, but then they started streaming what would be the test sample through the ZTF alert distribution system for 4 months, starting late 2022, sorry, not 2023. And these streamed alerts are actually in the forms of alerts, so this is what we wanted, but the training sample wasn't. So in order to avoid this mix-up of types and maybe the difference in the build-up of these 2 samples, what we call training sample for this work is the streamed alert sample, which is comprised of in total about 50-something million alerts, and we did a pragmatic split. The first year we used for training, and then we distribute this to the teams, well, which team download it actually, and do it whatever they want. However they want to train their models, you can do it, but then the last 2 years from the simulated data were kept in the central computing in France and to be used as a blind test sample. So I'll just jump straight ahead to the classifiers that we were trained for this data set. CATS is the one that I developed. It stands for CBPF Alert Transient System. This follows the old astronomer tradition of thinking of a good acronym and then trying to find words to fit it. It's a deep learning architecture, so you can see the deep learning here. It uses the light curves and the metadata, tabular data that Guillermo was talking about. Basically uses this type of metadata, both the extinction, which is always available, of course, but the photo Z and the transient redshift when available. If not, whatever, it doesn't matter. And the light curve, what is used as a light curve is basically the difference in days between the first detection, the first point, which could be a forced photometric point, and that point, the flux, the error, and the filter, it is in one of the UGRIZY. We did some parameter optimization, both in the number of units, the number of layers, the activation functions, et cetera, to arrive at the final model. So to quickly, I thought this is supposed to be an animation. Okay, I have a backup later if anyone wants to see it. The other classifiers I'll talk quickly. One is supernova, which also is a deep learning, but is a bit different from CATS in that also uses a recurrent layer, but it needs a balanced training sample. And so this comes, we'll see later that this caused some problems for it. And it was trained as a multi-class and also for a binary classes targeting some specific broad classes. And the early SN1A is, these were all adapted from ZTF. They are working in production in Think for ZTF. The early supernova 1A is designed to catch supernova 1A in its rising phase. You can see here, I'll maybe show later if you want to see it. So it only classifies alerts on the rising phase. So it's trying to catch supernova before the peak. Supernova 1A before the peak, it uses a feature extraction plus random forest using a thing called rainbow, which is a way to fit multi-band light curves, all bands at once. And finally, one we call the superluminous supernovae classifier, but actually it's supposed to work for superluminous and parent stability supernovae. It uses the same model, but the features are taken from a parametric equation that was obtained using what's called a multi-view symbolic regression on the light curve of a candidate superluminous supernovae. So I have a little bit of time, so just to run through the results. These are the results on the blind test set, which I call the year 2 and year 3. And you've seen a bunch of confusion matrices, but this is a bit of a non-standard way to present them, just to save space. So if you see, I don't know if you can see if the numbers are too small. This is CATS, so it targets the 5 broad classes, a multi-class classifier, and then we have the supernova broad class classifier. And I hope you can see here, whatever is not other is what the classifier is targeting. So this is the early supernova 1A, this is the superluminous supernovae classifier, and these on the bottom are the binary classifiers with supernovae, super N nova, targeting the broad classes. So just to explain this non-standard way of presenting confusion matrices, at each cell in the confusion matrices, the top row is normalized to the predictions, and the bottom row is normalized to the true values. So if you take the main diagonal, you'll see on top in bold the precision or the purity, and you see the bottom in italics the recall or the completeness. And you can already see here that CATS works very well for the supernovae, the variable stars, and the AGNs. It struggles a bit with the completeness for both the long and short classes, which is exactly the same ones that the supernova broad has issues with. And this could be due to our split, that we chose like a time split between the first year and the last 2 years. And again, this is the same problem that supernova has here for the long, and for the fast and the long class. So we are looking into this a bit, but this probably is due to the split that we did between training and testing. These are the most time-sensitive classes, long and short, fast and long. So now we have okay. So another thing that a broker will do it's doing right now for ZTF, and Fink is doing right now for ZTF, and plans to do for LSST, is to connect the interesting alert with follow-up facilities. And for this, we need to be able to at least classify one alert as quickly as the alerts as quickly as possible, the objects as quickly as possible. So what you see here is the evolution of the precision and recall, or purity and completeness, however you want to call it, as the number of detections grow, or the number of alerts grow. And you can see, I'm showing just for CATS, we have this for every classifier. You can see that for CATS, for example, for supernovae, you already have a pretty much 100% purity with less than 2-3 detections. Obviously, this includes force photometry. And also, you can get above 80% purity for all classes with less than 10 detections. This is 10 alerts. And this is counting all filters, right? It is not per filter. And finally, we have, 9 classifiers. What can we do with them? How can we combine them? Well, there are different ways to combine them. One of them is to use one broad classifier as a first step, and then you send them to the binary classifiers, like a hierarchical classification scheme. And this is what you see here, the result. This is applying CATS before the superluminous supernovae. So you take only the alerts that CATS classify as long, which is the broad class for superluminous supernovae, and then you get a slight better purity, and like the completeness is increases significantly. Now, the other thing that we can do is to take all of these binary classifiers and join them into one multi-class classifier, which is basically taking the highest probability. And then you see that the results improve a lot when you compare this to this, which is the broad class from the beginning. And finally, since we have 2 broad class classifiers that have different strengths, we can try to combine both the supernova, this one, with CATS. And you improve your results significantly, especially for these 2 classes, which the CATS and supernova had the most issue with. And so just a quick takeaway from this, you didn't see it, but this data set is very heterogeneous. The imbalanced classes, the light curves the alerts are very different from each other. The results are satisfactory. We're happy with it. I mentioned that there are two classes that are the hardest to classify. And one thing that comes up is that this confusion here that you see between the long and this are the same for both CATS and supernova. This might be due to some similarities that are intrinsic to the data set. I just mentioned quickly that you see here that supernova has a higher completeness, but lower purity than CATS. So depending on what you want to do, you might choose one of those differently. And finally, that combining different specialist binary classifiers is better than to have, in principle, better than to have a full multi-broadcast from the beginning. But what you need to do is to take care of the time that you need to process. Now, Guillermo already told us that LSSC will stream about 10 million alerts per night. And this will be thousands every 30 seconds. So we need to classify and ingest, process them, and redistribute them in this time frame. But of course, we don't have infinite computing infrastructure. So the FINT engineering team monitored how the throughput of the classifiers for these alerts were, for the test alerts were, and about 82% of the alerts were classified in less than 30 seconds, which is exactly what we need to get for LSST in principle, 90% in less than a minute. Just want to point out that we did not optimize anything. We're just going for the best results possible. And finally, the FINC developed a new service. Ease of data access was paramount to this work, and so the FINC engineering team designed a new service for anyone actually who wants to download elastic data. You can go here. It's pretty simple to use on a web browser, and you just need time to download it. But in principle, the service is very simple to use. So all in all, FINC is already working with ZTF, same as alerts. We have some, but LSSC will be completely different. So we need new tools to deal with it. We're working with simulated data right now because we don't have the real thing. We have 9 different classifiers for LSSC, which were adapted or created specifically for this challenge. We are currently working to optimize this and make them work within the time frame that we need. The engineering team developed a new service for anyone who wants to use it. And FINC is working to provide training at scale, because right now everybody trained it in its own resources. So thank you very much. If you want to visit FINC and know more about it, you can visit this. There are a bunch of tutorials. It's very simple to use. Thank you very much.
Thank you for a lovely talk, and we have time for 1 or 2 very quick questions.
My name is Hanoku, and thank you very much for the great talk. I was so happy to have a chance to learn about two alert brokers of LSST in one session. But I also know that there are still 5 to 7 more alert brokers of LSST to learn about. Yes. So do you know why they chose so many alert brokers? Is there an advantage they can get?
I think this is a question for the LSST.
I see.
I don't know if Guillermo knows it. I have no idea. This, as far as I know, it was a kind of a competition between, I don't know how many contestants and how the competition was done. But I mean, at least they try to spread the brokers around a bit, right? There's some in Europe, some in America, and some in South America. But I don't know the specifics.
I understand. Thank you so much.
Thank you.
Okay, we have a question on Zoom, I think. Can you mute yourself, or do we?
So I'm asking this question on behalf of an online participant. They're saying, do I understand that the alert is triggered best when you have about 10 data points? Do some classes of events require better time coverage than others?
Yes, it is correct. So if you go back here, this pretty much is the same for every classifier, that as the longest light curve, the longer the light curve, the easier to classify it is. And this, well, this is obvious if you think about it. When you see more of the object, it's easier to tell what it is. But one important thing that I mentioned is that we need to be quick, and we can be quick, at least for most of the classes. For example, this is the long class, which would include the superluminous supernovae, for example, which could extend for months. So if you have just a few alerts, you won't be able to say anything about it. You probably label it a normal supernovae, not a superluminous supernovae. So time is, especially for some of these classes, is important, yes.
Thank you.
Thank you.
Okay, and I think with that, we'll conclude this after lunch session. Let's thank all our wonderful speakers again. And I want to remind everyone, you can leave this here, and please ask more questions, reach out to the speakers during this coffee break, but also use the Slack and the online space to ask more questions. And we will start back here again in half an hour.
Good.
Hi, Damien, are you online?
Yes, I am.
Okay, could we try sharing your slides and
I cannot share right now because some other
Uh,
participant is sharing.
okay. Okay, can you hang on 1 second fast? Just need to get the person.
Was I fine?
That's what I'm working on.
I want to.
Let me. And then is Lindsay House online? And do you have Sandor Crook's presentation? Okay, so you're Lindsay. You're in person? Yes. Super. Awesome. Yes, thank you. Yeah, it was a bit hard to figure out that there was a switch, but happy that you're in person because there was some. Okay, good. Okay, so it's just this one.
I'm sharing my screen right now. I don't know if it's showing somewhere.
No, he's not. He's not next. There's one talk first.
Yeah, sure.
But we want to just check that it works.
Okay.
So it's going to be. Did you get this one?
Yes, I did get it.
Okay.
Is the sound okay, or do you hear me correctly?
We can hear you very well, which is good because that was
Okay.
the problem we had before. We now see you on the video, but we don't see your slides. Damien Chapon.
Yeah.
You can share your screen now.
I am actually sharing right now.
Stop and redo it, please.
Okay. Okay. Okay, I'm sharing. Do you see anything?
Okay, we can see it here, but it's not quite on the screen just yet, so hang on 1 second. And then do you have the first talk ready? This one? Yeah. But we need to make sure that it's working. We're just trying to get the screen to share. So one minute, sorry.
Yeah.
Damien,
Yes.
please can you stop your screen sharing and then redo it again, please?
Okay.
No, this one is now Lindsay House. So this, I think, is not up to date. Okay.
Okay. Sharing.
She's here. That's the speaker for the next, after his.
I'm not seeing you. I don't know why. I'm not seeing you. I don't know why. I'm not seeing your screen share.
It's on the WhatsApp. WhatsApp. That they've been sending. I'll send it to you. I'll send it to your email.
Yeah, WhatsApp.
So I think I sent a message. Here, Lindsay House. Lindsay House is the speaker replacing Laura too.
Oh, who's this? Is
But she'll put up her screen.
Damien.
You can say.
Yeah, that's me.
Okay. Pin him quickly.
But we should probably get started because we're going to be.
Okay. I can see you here this side.
Okay.
Yeah, but I'm not seeing you screen sharing. I don't know why.
Shall we start the last session?
I can see you, but the thing is I don't see your screen sharing.
Could you show the slide for the first speaker, Keiya Hirashima?
Yeah, he's sharing the side. Okay, I mean, let's start and then we can, as long as we'll figure out when we're going out. Okay, I mean, you can stop sharing and then we will do it on the next one, so it's fine.
Okay.
Thank you. So this is the final session of this focus meeting. The speaker is Keiya Hirashima.
All right. So, hello, my name is Keiya Hirashima. I'm from University of Tokyo, Japan, and thank you for coming back to this classroom in time. And I'm going to talk about the surrogate modeling for supernova feedback toward high-resolution Milky Way-sized galaxy simulations. So before going to the details of machine learning and simulation part, I briefly introduce the motivation or background of this research. So we care about mod-scale gas dynamics in galaxies and galactic evolution. So first of all, stars in galaxy were born in star homing region, which is very cold and dense gas clamp. And after a couple million years after those star was born, some of massive stars were exploding as a supernovae. And then this explosion is releasing chemical elements, and also by the massive thermal energy and the momentum drives the outflow and the turbulence in a galaxy. But still, this behavior of the outflow and the inflow is depending on the mass of the host galaxies, and we still don't know the balance between this star formation rate or the rate of supernovae and behavior of outflow, inflow, because we need the high-resolution simulations which can resolve the multi-scale gas dynamics. The other interesting from the observational side will be some of supernovae are triggering next generation star formation. So here is the observational result of Hubble telescopes, and then I just put the infrared observation by James Webb telescopes, and these multiple blue circles indicate the shell by multiple supernovae. And these shells are considered to be like suppressing star formation by tearing up star formation regions usually. But people found the molecular gas on the edge of the shells by compressing the gas by these superbubbles. So this may indicate supernovae can trigger star formation. But so to quantify those balance between supernova feedback or star formation rate, we have started developing the high-resolution galaxy simulations accelerated by the AI architectures. So the one of the challenges for the high-resolution simulation is that the multi-scale physics in galaxy. So for example, if we want to look at the galactic evolution in a galaxy, you may have to run the simulation over 100 million years because it's compared to the rotation time for the galaxy. But at the same time, to resolve the feedback from the supernovae, you have to resolve 1,000 years, less than 1,000 years in time-wise. And as for spatial resolution, it also has a big gap by like 3 orders of magnitude. So it's pretty multi-scale simulations. So if the simulation has multi-scale physics, it will confront the overhead of the parallel computing at some point. So here is the strongest scaling of gadget 4, which is one of the largest galaxy simulations. And this is the calculation time as a function of the CPU cores they used. So if they use more than 1,000 CPU cores, the calculation time is going to be saturated. So no matter how many CPU cores you can use, you cannot increase the mass resolution of the simulations. So to accelerate simulations, fundamentally, we started thinking about how to decrease the total number of calculation steps to increase the mass resolution in the galaxy simulations. So here's the idea of our architecture. So in a whole galaxy, in the simulation is calculated with 1,000 to 100,000 calculation nodes. And then every time supernova happens, the supernova and the surrounding gas is going to other calculation nodes. And then the machine learning model will predict the effect of supernova feedback 0.1 mega year after the explosion. And then the whole calculation box advanced by 0.1 mega year, the predicted distribution of particles and physical distribution is going back to the main calculation node. And then in an ideal case, we can fix the minimum time step as 2,000 years, which is 10 to 100 times longer than the pure simulations. So here's a model we used. This is the unit which is actively used in computer vision, and it's basically a supervised machine learning model. So given the initial condition around the supernovae, the model is predicting the shell of the supernovae and some distribution of temperature, density, and three-dimensional velocities in 3D. So, and also training dataset training dataset includes the simulation of supernova feedback in the molecular clouds. So these simulation mocks supernova explosion in the molecular clouds. So the initial temperature is 10 Kelvin, and mean ambient density is a little bit denser than the like is a density of molecular clouds. And the mass resolution is a little bit higher than the target Milky Way size simulations, because to increase the fidelity. So here's the one of the example of the prediction. So the upper figure are like pure simulation, and the lower ones are machine learning model accelerated simulations. So in the simulation, when a supernova happens, these particles around the supernova is going to machine learning model, and then machine learning model outputs the particle distribution after 0.1 megayear after the explosion. And then we test it, rerun the simulation with this predicted particle distribution. So here the right figures are like the rerun case. And comparing these two simulations, it can stably simulate the expansion of burst waves by the supernova explosion. We also checked other conservation law or momentum or thermal energy, but I don't have time to present here, so please check this paper or please reach out to me after this talk. And we already implemented this machine learning model in the galaxy simulation code. So could you raise your hand? Could you raise your hand if you think about on the left side is a pure machine learning model. Pure simulation. None. So if you think about, so if you think that on the right-hand side movie is pure simulation, could you please raise your hand? Okay, so some people think right-hand side is the more realistic or more physical, but actually this is the machine learning accelerated version. So by human eyes, it's already hard to tell which is the pure simulations or like kind of cheated by the machine learning. And this is a preliminary result, but here is the speed up we gained by using machine learning model for the supernova feedback. So the movie I showed is this case, because we don't, in the previous movie, I didn't use the 5V feedback. But if I use 5V feedback as well, including besides supernovae, this can be also accelerated by a factor of 4. So this number means like, so usually galaxy simulation takes several months to 1 year. So 4 times faster means you can save like half a year in the ideal case. And also we checked the star formation history. So the dashed line is a pure simulation case, and the solid line indicates the machine learning accelerated case. So its the discrepancy is like maybe 1 or 2 factor, by a factor of 2 or 1. So this is acceptable in because like these executable files are not identical. So if we compile this whole code in other like architecture, for example, this value can be fluctuated. So this is still under the range of these like fluctuations. So it's not so far from the like test case. Also, we checked outflow rates in terms of mass loading factor and energy loading factor. Mass loading factor means mass outflow rates from the galaxy in the direction of z-axis and uniformed by star formation rate. Yes. And also the energy loading factor is the, it's a very similar concept, but the energy loading rate uniformed by the energy of supernovae per year. So if you look at in a blue solid line and dashed line, it's still in the same range of the values. And also, this red line indicates the other, it's gained by the other calculation code based on gadget 3 from other group. And this, our result is also consists of other simulation by other methods. So it's very consistent, even though we use a machine learning model. So here's a summary and the future direction. So we have developed the machine learning model to accelerate supernova feedback toward increasing the mass resolution, and eventually in the future we're hoping to develop the star-by-star galaxy simulations with a Milky Way-sized galaxy. And so far, the simulation in the galaxy can be accelerated by a factor of 4. And in the future direction, we are trying to run the heavier galaxy simulations and other feedback model like AGN feedback in the cosmological simulations. All right, thank you so much.
Questions?
That's great job. Could you go back to the mass loading factors? Yeah, this one. Because I was looking at the numbers. If you look at it to 150, then the change can be more like a factor of 10, I guess, in the orange lines, right? So can that be an issue, or is this like just one system, one simulation you have? Or like, have you done this for like many simulations, maybe get scattered? Because if you just look at short times, then maybe it's a factor of 1 or 2. But by looking at this, I can see that it can vary by large amount at different times.
I can't say like a strong statement here, but the one of the reason we see like a very large scatter is because we just learned the 250 million years, so which is not long enough to consider the to see the effect of like feedback and outflow. Because if there's the like bursting star formation at some point, maybe around here, and then you see like strong outflow there, and then suddenly the stellar feedback is going to be come down around here. So maybe that's the one scenario to see the like this like large scatter. So if we so I'm still keep running this simulation. So if we get more longer snapshot of the simulation, then we can discuss that scatter, I think.
Okay, maybe one more short question. If not, let's thank the speaker again.
Thank you.
Thank you. So the next speaker is online, I think. So Damian, are you ready?
Yep.
So, so our Zoom has not been ready yet on the screen. Wait a moment.
Okay, from Zoom for the previous speaker, your DL prediction must be sensitive to the scale you choose, linear resolution. Very promising approach, by the way, crispy.
Thank you. But it's a question, comment, just comment.
Is it sensitive to linear resolution, to the scale you choose?
Linear resolution, yes, yes. And basically the like small scale of the like length of the voxels, I think it's very sensitive. But it depends on what you want to see. But I want to see the outflow and the star formation rate in the galactic scale. So, so maybe, but I saw some fluctuations in the outflow rate. So, yeah, so that's my comment.
Okay, thanks. Thanks a lot.
So we still have some problem to project the screen of Zoom.
Okay, I'm sharing the screen, but
Yeah, it's coming.
Okay.
But it's not
Oh, I
the
see.
screen of Zoom.
Okay, if you can just speak. Demir, we can't see you, but we can see your presentation. So if you can just go ahead and start, and then hopefully they'll be able to get the video on.
Okay.
That's okay. Thanks.
Okay. Hi, good afternoon, everyone. My name is Damien Chapon. I work at CEA in Saclay. First, I would like to thank the members of the organizing committee for inviting me to this IAU General Assembly and to this focus meeting. Today, I'm going to talk to you about the Galactica database, which is an open, generic, and versatile tool for the diffusion of numerical simulation data in astrophysics. So to start, my day-to-day work in CA is actually to answer this basic question: how to handle high-volume data in computational astrophysics at the exascale era. So it's at the crossroads between high-performance computing, open science, big data, and high-performance data analysis. Today, I'm going to focus on two very specific topics, which are the last two ones: the share and reuse data in the specific field of computational astrophysics. With my colleagues in the astrophysics department of CEA, all of them doing a lot of very different type of simulations with the theoretical models and 2D, 3D numerical models in a wide range of scientific applications, from cosmology down to planet formation and exoplanetary atmospheres, as illustrated by these few images. Well, for these colleagues of mine, there was no, it appeared at some point that there was no common tool to share and to disseminate their numerical simulation data to the scientific community for all their different scientific applications. So there are a lot of databases in general in astrophysics. You know, of course, a lot of them in astronomy, but there are a few of them also in computational astrophysics. And the main trait they share is that all of them focus on one very specific type of applications, for example, turbulence or interstellar medium, star formation, cosmology, interacting galaxies, etc. I mentioned, for example, the Illustris database, the CosmoHub cosmology database. But there is no tool, no generic tool to share data coming out of simulation, numerical simulations. I also have to mention that in the last 10 to 15 years, there have been quite a few developments in terms of software technologies for big data applications. Here, in the context of what I'm going to talk about today, I will mention the Daiquiri framework, which was a nice mutualization effort in terms of astrophysics-specific web application framework. There is also the asynchronous task management system called Celery, and of course, well-known database technologies like Apache Spark or Hadoop. Of course, a lot of talks this week talked about Jupyter notebooks and Jupyter Lab environments to share software in the scientific community. So I won't go any more details about that. So what we decided almost a decade ago was to create our own open research data platform in computational astrophysics. So since 2015, we developed the Galactica web platform for open science in computational astrophysics. It's available at the address www.galactica-simulations.eu. It's completely generic. It's collaborative, so it's multi-contributors, and it's open and free. First, it was initiated by an European Research Council project, funded project called MAGMIST and these days EcoGal project. And since 2018, it's hosted by the Heidelberg University Cloud, HiCloud. So the main objective of that initiative was to promote something computational astrophysics are a bit lagging behind their astronomer colleagues, which was to promote simulation data sharing and reuse in the scientific community. So the main idea is to, for example, allow theoretical model validation, numerical model comparisons, to enhance transparency and reproducibility in science, but also to help astronomers prepare the observational campaign and perform some comparisons between theoretical models with already available astronomical data. And also to provide a tool for small projects without the resources to publish their data on their own platform or website, to be involved in this open science effort via this shared infrastructure, which is Galactica. So the general concepts of the Galactica web application we developed. So the idea is, of course, to have something generic to fit the needs of any application domains in astrophysics. This application is based on the simulation data model standard by the International Virtual Observatory Alliance. It's developed with the Django web application framework. It's a Python framework well known in the field. It's collaborative, so it's multi-contributors and multi-profiles. You have data publishers publishing their project online, and you have data readers who only want to access data published on the platform. But what kind of data are we talking about? So here I'm going to make a quick distinction between different types of data. First, there are metadata, so very lightweight, kilobyte size data, text, numerical values, URLs, mathematical formula, etc. Then you have reduced data sets, either uploaded by the physicists to produce the simulations or generated on demand by the Galactica infrastructure. And all these are typically 2D images, plots, spectrums, PPV cubes, tabulated data, object catalogs. And these are typically in the range 1 to 100 megabytes per item. But so these two types, A and B, of data, metadata and reduced datasets, will be hosted on the Galactica platform file system. So the Galactica platform file system is very light and quite cheap in terms of finance, because it's only a few tens of gigabytes of storage. Okay, but the main question is, what do we do with massive raw simulation data that are generated by the simulation snapshots, which could span in the range 1 gigabyte to hundreds of terabytes of data per snapshot. So to solve this problem, we deployed an on-demand massive data processing architecture through online web services on Galactica, and this led to the development of the Terminus server, which is an asynchronous data processing task manager. It's a thin overlay over the Celery task management platform, and it uses RabbitMQ as a messenger. So the architecture is as follows. You have the Galactica web application, it's Django web application. All the metadata is stored in the MySQL relational database backend. And all the reduced data sets, either uploaded or generated, is stored in the Galactica file system in the 40 gigabytes of disk available on the web server. And this Galactica application communicates with one or many Terminus data processing servers, hosting both computational and storage resources with Celery workers waiting to execute data processing tasks on the raw simulation data hosted on the disk of that server. So here I show you a simple image where you have one Terminus server coupled to the Galactica, but actually you can couple as many Terminus servers as you want around the single and unique Galactica web application here. And if you do that, you immediately remove the need the requirement to move around massive simulation data. You actually let them live where they usually are in astrophysics research institutes or tier 2 or tier 3 supercomputing facilities, where actually the initial scientific analysis was performed, and also where initially the libraries and data analysis pipeline is already installed and deployed. So you don't need to move around data. You don't need to deploy anything anywhere. You already have all the software installed where the data are, and you already have massive storage in a distributed ecosystem of terminus servers. So in terms of data processing service, typically you have an online on-demand job request infrastructure to answer specific requirements of the scientific community to do, for example, sample extraction, 2D or 1D projections, synthetic mock observations, PPV data cubes, whatever. And the user has absolutely no need to have any knowledge of the data formats the simulation were generated in, and no need to install any software to read the data. So everything is happening in the backend, and we encourage data products generated by the architecture to be generated in standard formats, for example, HDF5, FITS, PNG images, and so on. And of course, multiple terminus server instances can be hosted in different institutes. And with that, you end up with a distributed data processing ecosystem with very high scalability, security, which complies with FAIR principles. Since you don't have to buy new disks or new CPUs, you only share existing resources in astrophysics research institutes, and you only ask them to commit to share some of their storage and computational resources in these open science efforts. You don't have to buy new hardware to do that. So it's very cost efficient also. And you also ensure a great governance because in compliance with the local policies or project by project data management plans, every physicist and every research institute has complete control over the data and they want to share and the services they want to provide the community. And they also have complete control over the allocated storage and computational resources they are willing to share with Galactica. So what does it look like? This is the homepage of the Galactica web application. Here you have a project sorted by categories. You have at the top in the top navigation bar some links. Publish my project, share massive data. I will put the links at the end of this presentation. You also have a search engine to search a simulation or project by name. If you click on the category, you also have a list of projects in that category. So for example, this is the star formation category project page. And you have links to specific project pages where you have the full description, the numerical setup, the links to the publications. You can put images, mathematical formula, and you have, of course, a list of simulations inside that project. So in the simulation page, you can describe your full numerical setup with parameter values, resolved implementations of the applied physics, the numerical solvers, etc. And then you have a collection of snapshots of this simulation. And to each simulation snapshot, you can attach reduced data sets, for example, here a JPEG image. You can have object catalogs. You can download the complete archive of these products. And you also have a list of on-demand data processing services bound to this snapshot. So for example, the object catalog this is something quite similar to what you will find, for example, in the Illustris database. So here you can filter out and search online catalogs with parameters and range of values, and then export your filtered result of your search in various standard formats like FITS or HDF5, JSON, whatever. So this is quite common. This resembles what you will find, for example, in the Illustris database. But the main difference is that in Galactica, you will have object catalogs of completely different types. You can have catalogs of galaxies. Here you have protoplanetary disks. You can have also sunspots, protostellar cores. You can have galaxies, dark matter halos, galaxy clusters, whatever. So it's completely generic. Here, for example, you have the page where you have on-demand data processing service available for a given simulation snapshot. And when you click on one of these services, you have a dynamically generated user job request form where the user can select his own parameters for this service. You can have here the full description of what is the service, what is the parameter, the version of the data processing pipeline, etc. can be documented. There is no need to install anything here, and the user doesn't have to have any knowledge of the underlying data format. So when the user clicks on the Submit Job Request button here, it triggers a message to the RabbitMQ messaging server. The RabbitMQ messaging server routes the message to the Terminus server that is actually hosting the simulation data and where the service is deployed. It processes the data processing task. It can be sent to a Slurm job queue, for example. And when the data product is generated, the data product is uploaded back on the Galactica file system, and the Terminus server sends a RabbitMQ message that is routed back to the Galactica web application. And when that is done, the Galactica web application can send a notification email to the user to inform him that, okay, his data product that was requested is available to download. So when the user is connected, he can have access to in his own user menu to the listing of his job request with the full information, the target data, the parameters, the job execution time, etc., and the status of his job evolving. And when his job fails or succeeds, he will receive a notification email. And when it succeeds, he will have here in green a link to the data product that was requested, available for download. So this Galactica web application plus the Terminus server piece of software are two important ingredients in this landscape. But there is one, of course, a missing ingredient here, which is something to help astrophysicists publish their simulation on the Galactica web application. So of course there is, I don't have time much to show it in details, but there is an administration interface available to authenticated users on Galactica, of course. But there is also an additional tool to help physicists document their project, which is the Astrophysics Python package, which I developed. This is an offline project documentation API, also implementing the simulation data model IVUA standard. And it produces HDF5 study files that you can immediately upload on Galactica. And once it's uploaded on the Galactica platform, all your project pages are immediately deployed on the web. So a quick example on how this is working. So here I put the links to the documentation, the PyPy repository of the astrophysics package, and a few code snippets now. So for example, you have an example to how to create a project with astrophysics. It's only 4 lines of Python. How to create a simulation snapshot and insert this snapshot into a simulation. Again, a few lines of Python. Then another example, you have the creation of a data file with a JPEG file attachment that you insert in a snapshot in a few lines of Python. And finally, a Terminus data processes service binding on a simulation snapshot in less than 6 or 7 lines of Python. So all this API with astrophysics can be integrated into your scientific analysis pipeline to document your project ready for publication in Galactica along your scientific analysis results generation. So you can integrate it in your pipeline. As a summary, so we end up with the Galactica generic open science platform for computational astrophysics available at this URL. It's available for computational astrophysicists and astronomers. It's based on an IAU standard, and it's a centralized sharing hub for computational astrophysics data in a distributed data processing ecosystem with multiple Terminus server instances, so asynchronous data processing servers hosted in different astrophysics research institutes. The Terminus server is very versatile. It is fully compatible with any type of code, with any type of data processing library, and to handle any, to generate any data product type. It's low maintenance, it's highly scalable, very cost efficient, participative open science platform for all astrophysicists. And then the astrophysics package to help physicists upload their data on Galactica. So last, a few advertisements. So here I put some links if you want to contribute to the Galactica ecosystem, and email address if you want to request a user account. And then last, so the next training event will be held in Paris, in France, in November 12th, 2024, the Galactica Training Day. But there will be also a remote online session, so if you want to participate, feel free to get in touch by email. Thank you.
Thank you, Damian. Great work. So question from the audience? Okay.
Thank you very much for the presentation. It's very interesting to see. You said in the last bit of the presentation, you mentioned or you invoked the idea of an ecosystem. And I'm curious to know whether or not the platform will include some way of preserving the connections between different simulation data sets. So will there be some way to know that data set A was a precursor to dataset B, and this was then improved in dataset C? Is there some way of that lineage metadata is encoded?
Okay, so thank you for this question. So there is a possibility actually, if for example you run a train of simulations in, for example, in cosmology or in galaxy formation or whatever, there is a possibility to actually set links to other simulation or project pages inside the text itself of the project page. For example, if you have you can cross-reference with the internal Galactica web application links, simulation with one another or project with one another at will. Basically, there is no limit. You have complete control over the displayed text on the Galactica page content, I mean the body of the page. So yeah, there will be a possibility to cross-reference simulation with one another with internal links basically on the web platform.
Thank you.
So other questions? So I have one question maybe. So is it also possible to use like a normal server, go to SSH and run some analysis code? Or that's just on the Python script?
I mean, you mean from the Galactica application itself, or what kind of workflow are you thinking about?
I mean, we want to analyze one data set, and for one data set, can we access via sort of Python script, easy way to do, well, maybe some people, but yeah.
Like in a Jupyter Lab environment and load data, and so that's not the architecture that we deployed. The main idea is that I mean, in the worst case scenario, huge simulation data sets can reach hundreds of terabytes of data per snapshot for some cosmological simulations, for example. And this kind of data is very expensive to post-process. So the idea is that instead of executing some remote data processing online in a Jupyter Lab environment like that, what we propose instead is to provide the scientific community the possibility to extract some subsample of data, for example, in a subregion of the cosmological simulation. If you're interested, for example, in a specific, I don't know, galaxy clusters in a wide, very large cosmological simulation, you can extract a subsample of data in a three-dimensional data cube, for example. Then you can request this kind of data product on Galactica, on this particular cosmological snapshot, and then do the custom scientific analysis locally after you retrieve this 3D data cube on your local file system. And you can repeat this process at will. I mean, if you are interested in a lot of objects in a given simulation, you can submit as many job requests you want to do some parametric analysis or statistical study on a given set of simulations, for example.
Okay, thank you. So, question from.
A question from Zoom from Chris. Do you have control over the resolution of the data product? For example, to compare low resolution calculations to high resolution ones?
Yes, actually, there are a few data processing services available on Galactica on some simulations right now, in which you can, for example, you can generate 2D gas surface density maps, for example, of hydrodynamical simulations, 3D hydrodynamical simulations, and you can, of course, select the size of the region you want a map of, but you can also generate a map at a user-defined resolution. So you have in the data processing service the possibility to select the spatial resolution at which you want to produce your 2D projection, for example. So, and this is provided by the astrophysicist community who offer the simulation data sets and the associated service, data processing service on these data sets. And the sky is the limit. I mean, you can set as many. I mean, you're asking about resolutions, but there are a lot of other parameters that you can choose to include or not to include in a given data processing service. And basically, Galactica lets you define as many parameters in your processing services as you want. So it can be very custom tailored to fit any requirements from the scientific community.
Okay, thank you, Damian. Time is up. So So the next speaker is here again. Okay. So yeah, the slide is ready. So the next speaker is Lindsay House. Oh, it's not.
Cool. Okay, how about now? Okay, great, cool. So hi everyone, thanks for hanging in this afternoon session. I'm gonna be talking to you guys a little bit about unlocking astronomical discoveries, harnessing Zooniverse and machine learning for large data sets. And so my name is Lindsay House, and my home institution is the University of Texas at Austin in the States, but I've been working with Zooniverse this summer. And so I'm going to talk to you guys a little bit about what Zooniverse is. So for those of you that aren't familiar, Zooniverse is the world's largest online platform for cloud-sourced research. So what that means is we are a host platform for getting the public involved in astronomical research, or really research in any field. Our core team comprises about 20 people based at Adler Planetarium in Chicago, at the University of Oxford, and the University of Minnesota. And so since 2009, our community of more than 2.7 million registered users has had about 800 million classifications across hundreds of projects. We worked with hundreds of research institutions around the world and translated these projects into different languages that have led to about 400 peer-reviewed publications. And so as I talk about citizen science or participatory science, I'll use those terms interchangeably. I want maybe you guys to think about how you could use citizen science or participatory science with your research as well. And so I'll be talking about the intersection of those two. So just a little overview about what I'm going to talk to you guys about today. Obviously, I'm going to be focusing on machine learning and citizen science, how it's already been used within citizen science, how we might think about using it in the future as we're going to have larger and larger data sets moving into astronomy and the future of astronomy. I will talk about the example project or an example success, which is Dark Energy Explorers. So I'm the project lead for Dark Energy Explorers that uses data from the Hubble Telescope Dark Energy Experiment at McDonald Observatory in West Texas. So we'll talk about how we have had a successful use of participatory science and machine learning to help enhance our science goals with the Dark Energy Experiment. And then I just want to keep a part of the conversation, maybe some of the risks and the rewards as we're moving into this new field of machine learning, and making sure that we're talking about some risks and rewards that come with integrating these methods into our research. Cool. So as we're moving through, I want you guys to know the different task types that we offer at Zooniverse. So we have a free project builder that's open for any research teams or research scientists. And so our philosophy has always been to build tools for specific use cases and that generate the science and then generalize from there. So we have things like decision trees that can have different tasks embedded in. We have multiple marking and drawing tools. So if you're looking at galaxy morphology, or if you're looking to answer different questions like that, they can see actual images and mark on those images. We have surveys or filter tools, things like checkboxes, drop-down boxes that can be used that the public will actually interact with, and they will see that data and then be able to make a decision from those different images. Then we even have transcription and annotation tools. At Zooniverse, we have projects across all different disciplines, but could still be useful within astronomy to have these transcription and annotation tools paired with your machine learning work. So how have we used machine learning already on Zooniverse? We're here because we're talking about this large data problem that we have in astronomy. And so some of the proposed solutions that we've used at Zooniverse is our crowd-generated labels as training data for machine learning, volunteer review and validation of machine-generated output, using machine learning as a first pass for data pre-processing for the human-in-the-loop efforts. So similarly to the one before, maybe closing that loop using machine learning as well as humans to look at these objects, and then kind of closing that loop and using that as a triage process. So those human-validated objects would then be fed back into the machine learning model to create a sort of a validation process. And then lastly, combined approaches, and that's what I'm going to talk about today that we've had success using with our project. But I've also put the link up here for the full paper if you're really interested in some of the other ways that we've used machine learning in Zooniverse. So yeah, I'm excited to talk to you about this project example, Dark Energy Explorers. So I launched Dark Energy Explorers my first year grad school, which was February 2021. So it's pretty exciting. We have been going for about 3 years now. We have about 17,000 volunteers that come from about 150 countries all around the world. We have materials in English and in Spanish, and we've had about 6 million galaxy classifications from our project. And so the data that you see is from the Hobby-Eberly Telescope Dark Energy Experiment. We're an untargeted survey, and we will collect about 1 billion spectra, and we need about 1.2 million Lyman alpha emitting galaxies to meet the specifications for our dark energy experiment. We're a baryon acoustic oscillation survey, so we're using those LAEs to track large-scale structure. And what we do with Dark Energy Explorers, I mentioned we're an untargeted survey. So rather than pointing at specific targets in the sky, we're pointing the telescope up. We're collecting data across a specific swath of sky for many, many years. We actually just had our last data taken about last week, which is pretty exciting because we started in 2017. So we have a lot of data to sort through, and it's our responsibility, and that was this big problem that we were running into. So that was why we launched Dark Energy Explorers, to get the public involved to help us classify. But we must train them first, right? They have to know what they're doing. So Zooniverse makes it really easy. You create a tutorial, and so you can see here, it has a button for the tutorial, and it walks them through step by step how to look at all of these data, how to look at the images, how to look at the emission line, look at a flux map, and tell us whether it is a real galaxy or something that we want to throw back or get rid of our sample. And so in our case, we've kept it a binary choice. So it's a simple swiping right for a real galaxy or swiping left for a fake galaxy. And so while it's really exciting for the public to look at these astronomical sources, it's kind of this symbiotic relationship because it's great for us because then we get to see where our artifacts, where our false positives, and where our contamination lies. And that's really important for us as we use it in machine learning. So each source goes through Dark Energy Explorers and is looked at by at least 10 different participants. So that's how we create some validity. And we average those classifications to create this probability that a source is a real detection by human visual vetting. And so then we use these probabilities to interpret the machine learning work. So this is the specific example that I used. We use TSNE, which is an unsupervised machine learning algorithm. So we're using it on the post-processing aspect, and we're incorporating those labels after to interpret the machine learning work. So here's an example of what something might look like with machine learning and, with citizen science and without citizen science. So you can see over here on the left, this is what our machine learning algorithm looks like. Whenever we input our spectra, we get this black blob. It's not super exciting. And essentially, it's taking that high-level data, reducing it down to 2 dimensions to something that we can visualize. But with the use of citizen science, we can add color to this plot, and we can actually interpret some of the meaning that we're getting from this clustering. And with that probability that I mentioned, we can see here a probability of 0 means we have 0 probability from all 10 or more of our participants that this is an artifact or this is something that we want to get rid of from our data. But this up here, everyone agreed, so which would be a probability of 1.0, would mean definitely this is a galaxy that we want to keep in our sample and something that we want to use for that dark energy science. And so you can see this specific combination. It has been more accurate than machine learning or citizen science by itself. So trying to use these synergistically could really lead to more accurate and efficient science. Cool. So I just want to lastly highlight maybe some of the risks and rewards as we're moving in to this new field of AI and machine learning. When incorporating some of these methods, over-optimization is always something to consider, leading to decrease in participants' enjoyment. Lack of human oversight could lead to a decrease in data quality, or inappropriate use of machine learning by teams without internal expertise. So while all of these are high risks, I think having this as part of the conversation as we move forward into AI is always important, just to make sure that's why we're here in this session, to learn more about machine learning and make sure that we're being responsible. But in addition, some incredible rewards. So allowing participants to focus on more advanced or interesting tasks. It's been really cool. As part of Dark Energy Explorers, we have 17,000 people from all over the world that are classifying like real galaxies that are coming from a telescope, and they're feeling very empowered to be a part of this research. Better data models leading to higher quality data. It really is more efficient and accurate for us, especially with those artifacts. And so this creation of shared infrastructure leading to increased accessibility in machine learning tools. I think also as citizen science, it's really cool way to integrate with your machine learning, and also a really great way to build trust with the public as we're moving into this future of potential misinformation. So I just want to lastly take a moment to highlight also maybe some other sessions that we have with Zooniverse coming up. We have our using Zooniverse to enhance classroom engagement with a suite of new education tools, which is tomorrow. We're unrolling some new education tools if you're interested in using citizen science in your classroom as the semester starts. You feel free to reach out to contact@zooniverse.org to be added to email lists and things like that to get those as an educator. And then lastly, next week we have a equity inclusion through participatory science in Zooniverse next week. But yeah, with that, I will take questions.
Thank you. So, any questions? Okay.
Thanks so much for the great talk, Laura. I always love citizen science talks. I had 2 just clarification questions. The one is I just wanted to a bit better understand the HitDex survey. Is it basically, you said it's untargeted, so is it just a drift scan? You just take a spectrum of anything and most pixels are just nothing? Okay, so that's
we're a spectroscopic survey. We're just collecting data every night, specific spots.
Is it slit spectroscopy, or is it, so it's not an IFU or anything? Okay, cool. So yeah, I can understand being overwhelmed by that quantity of data. That's great. And then with the TSNE, did you run a TSNE on the raw spectra, or did you do anything like a PCA or anything in between?
Yeah, no, great question. That's okay, you can imagine. Yeah, so no, so what TSNE does, it's essentially if you're familiar, high dimensionality reduction algorithm. And so, yeah, we take the spectra, we make a cut around the emission line. So it's about 50 elements, spectral elements that we input into TSNE, and that's it.
Okay.
And then it reduces it down to something of 2 dimensions that then we can plot, and that was what you're visualizing.
Okay, and sorry, I'm hogging the mic. How do you identify the spectral line? Is it just a signal to noise?
Yeah,
So
absolutely.
around the brightest thing, and then you throw that to TSNE.
Yeah, exactly.
Okay, brilliant. Thank you.
Yeah.
Thank you, Lindsay. Very nice talk. So we know that people like looking at galaxy images from Galaxy Zoo. How do you get people to look at spectra?
Yeah, great question. I have been amazed at how much people love looking at spectra. I think maybe to us, it could be a little bit boring compared to, a beautiful galaxy image that's got great color, structure. But I mean, yeah, the public is really excited about astronomy and especially dark energy. I think we have made a lot of partnerships with like local libraries. I've done a lot of work with like developing K through 12 materials and worksheets and things like that. So if any of you are interested in incorporating in your classrooms, we have all of those and videos and stuff like that to make it really easy. And then they kind of pair it with some sort of, lesson on galaxies or depending on the level, lesson on how like, expansion of the universe and that kind of thing. But yeah, we've been pretty surprised at how many people like looking at spectra.
Okay, so we have to move on to the next speaker. Lindsay, let's thank Lindsay again. Okay. So the last speaker is Sandra Crook. Okay, let's start.
Thank you very much for the introduction. So I realize I stand between you and dinner, probably. So I'll try to keep it short. My name is Sandra Crook. I'm a data scientist in the Archives and Data Science Division, the European Space Agency. And I'm going to shift the topic a little bit and go back perhaps to topics that were discussed more on Tuesday. I'm going to talk about science platforms and the science platform that we've been developing at ESA, and it's called ESA Data Labs. So a little bit about where we are, what we do. This is the European Space Agency Astronomy Center, ESAC, one of the main establishments. The main science establishment of ESA is located in Madrid or near Madrid, next to this beautiful castle. We have a castle on site. And ESAC hosts the Science Operations Center for the ESA Astronomy and Solar System missions and the ESA Science Archives. So this is the place where your data from ESA missions is held. There are over 20 data from over 20 missions in operations or in post-operations phase, in so-called legacy phase. And currently we have around 1 petabyte of data in the archive. But this is changing very rapidly, as you probably know, with missions such as Euclid, which was launched last year, which will add more than 10 petabytes over the next 6 years. So there is this big data challenge that we heard about already. And we have to change the paradigm from bringing the data to the user to bringing the user to the data. You will not have the possibility to download all this data onto your computers. But it's not only about big data. There's lots of data in the archives already, and lots of people using the data in the archives already. So you know that Hubble Space Telescope has been taking data for over 33 years. Now, if you look at the number of publications with the Hubble Space Telescope, you'll see that right now, there are more publications with archival data than general observers. So then astronomers proposing for data, getting their data and publishing their papers. So we're slowly moving in this era where we're using more and more archival data for our publications. And someone from ESA, Guido De Marchi, looked at these statistics across multiple missions and found that this is not only true for Hubble, but for all ESA missions. So both planetary astronomy missions. We are publishing more papers with data in the archive, with archival data, than with general observer missions. So this is why we're developing ESA Data Labs, both for the big data challenge to allow users to bring their code to the data, to process, for example, Euclid data, but also to access data from the archives directly. And I know we've heard many talks about high-performance computing simulations. Data Labs is not a high-performance computer, but what we're doing is we're providing resources sort of similar to a laptop, a powerful laptop to the users to access and process, doing the data analysis close to where the data is located. So these are the goals of the platform. One is to boost the research productivity. We know we need a lot of infrastructure for our research. So what we want to make sure is that astronomers do not care about what the infrastructure they use to run their code. They also don't care about the system development side and focus on the science and the science development. So we're using technologies such as Kubernetes, Docker, and Jupyter Lab. Then secondly, the goal is to boost the access to data, of course. So you want the platform to be co-located with the data itself and be able to mount data from various missions like James Webb, Euclid, JUICE, etc. And thirdly is to boost research collaboration. So we notice that most researchers, as probably everyone knows, they work in teams, and you want to share your data, you want to share your code together. So we have team workspaces that enable you to share all of this with your collaborators and work simultaneously. How do we do this? So we have data volumes. So these are the data that you actually find in the ESAC archives, which you can mount in Data Labs. So this is, for example, the data from the public data from Euclid, the early release observations that were made available last November and this March. So you're able to access, for example, data such as this one, but also a lot more. We provide a list of data labs. So these are software packages that were created mostly by our missions using standard software, data analysis and data processing packages that are relevant for the various use cases across the various sciences that we cater for. So there are packages, for example, created for Gaia mission, for Euclid, or for XMM. And I'm not going to go into detail because Peter here in the audience will present a poster on his work, and the team's work on enabling X-ray astronomy from anywhere as one of the data labs. I think the session is tomorrow morning. We also have desktop-based applications. So these are GUI applications. So going beyond Jupyter Labs, we have your astronomer's favorite TopCat and DS9. And the new functionality that we added last year is the capacity or the functionality to build your own data lab, to do it yourself. So if you have a Docker file, Docker container with your application, or if you're using Python, then you can simply upload your packages or clone them from GitHub and make your own application in data labs that you can then share with your collaborators or make them public in a public repository, a bit like an app store for science, where you can share this code with your collaborators and publicly across all the users. We also have a pipeline orchestrator that allows you to connect various pieces of code together, have access to input-output files, parameter files. For example, this one is for James Webb Space Telescope. It's the MIRI processing pipeline that allows you to pull calibration files directly in the pipeline. We have dedicated help pages, lots of pages of instructions on how you can start a data lab, how you can build your data lab, also videos, and there's a dedicated service desk that's available here. About the community, about the users, who are users. So we ran various workshops, first dedicated to how to use data labs. What is data labs? We had those, I think, starting in 2022. Then last year we had workshops where we used data labs as part of the workshop. So we had a Euclid hands-on workshop with 150 participants in Copenhagen last year, where we taught users how to access Euclid data, how to make use of Jupyter notebooks to introduce them to how to analyze Euclid data. Then we were invited to the JWST summer school in Heidelberg, where lecturers use data labs as a way of disseminating the software, the material to the students and train them. We also had a dot astronomy workshop at ESAC. This picture is from there, where we made use of data labs for hacks, for making projects together in small teams. And we have two more workshops coming up. One is natural language processing. If you're curious what that has in common with the rest, you can ask me later. Then we also have a Data Labs hackathon coming up in January next year. So in total, we have 1,200 registered users on the platform. 950 of them have accessed and used data labs at some point. And about active users, I know we had this discussion on Tuesday, what does an active user mean? We have about 50 to 60 daily users, so users who log in daily and use data labs. So what about example use cases? I'd like to focus the last few minutes on a couple of use cases. One that is close to my research interest, and that is galaxy morphology. This is a project where we used David Orion, who was a PhD student at that time, used ESA data labs to create a large catalog of interactive galaxies using the entire Hubble archive as a survey. So again, 30 years of data. What he did is he took the data volumes from Hubble, plugged them in, got his code to create cutouts, millions of cutouts. And then he's used something called the ZooBot. It's a deep learning foundation model that was developed by the Galaxy Zoo team, by Mike Walmsley. And we've heard about deep learning in the previous sessions. So what he's doing is basically is trained on 1 million galaxies from Galaxy Zoo and is able to predict very accurately the morphology of new ones. So he's used the ZooBot software, which is now available in data labs, to classify merging galaxies and predicted about 20,000 interacting galaxies with high confidence. So we wanted to create a very clean sample of merging galaxies. And he published a very nice paper, also finding some strong gravitational lenses as byproducts and protoplanetary disks. Now, the cool thing about this project is it was done in 3 months. So since it was done in 3 months as part of the archival research program, where scientists from outside ESA come to ESA for 3 months to work together with the archives. So in 3 months, he managed to run his code, create the cutouts, run ZooBot, and have a draft of the paper. Then it took a bit longer to get the paper out in the publication, but we know that's the process. Now, continuing a bit more on this topic, but a bit more recent, last week we launched Galaxy Zoo for Euclid. You know, I think you all know about Euclid. It's a huge mission. It's going to image 1/3 of the sky, hundreds of millions of galaxies with resolved morphology, the largest catalog of morphologies that will be ever created. So it's enormous science impact. But we need classifications for those galaxies. We need to have a big catalog of galaxies classified. And of course, the answer for that is deep learning. We have ZooBot. We have a good classifier that we can use and plug into the pipeline. But we have a problem. The problem is that there are no galaxies classified from Euclid. There's always this domain shift in machine learning where you have to have a small sample of galaxies that you classify from the survey itself to learn the instrument properties and so forth. So what we did is we used ESA data labs again to create a large number of cutouts from Euclid data itself, and then fed this into Galaxy Zoo. So now if you go to Galaxy Zoo, you'll be able to see Euclid galaxies. And if you care about science, if you care about galaxy morphology, please share the website to collaborators, friends, your parents, anyone. We need 500,000 classifications by the end of August to get the pipeline working in time for the data release. So please help us. Yes, and there will be there'll be a talk about Galaxy Zoo and the 17 years of Galaxy Zoo, actually on Monday. This has changed by Karen Masters. So just to conclude about the next step, what are the next steps for ESA Data Labs? One is we would like to enable more AI machine learning use cases. We would like to plug in GPUs, and this is something we're working on right now, is to add GPUs to the platform so that people can not train maybe, but fine-tune their algorithms and make it work on new data. Then we would like to expand Data Labs a bit. So we have colleagues who work on other domains like Galileo navigation satellites. They also have science data. We have a parallel platform, which is called GSSE now. So we want to find a better integration between the two. We also want to better integrate with the archives. So you can, for example, go to the archive, click on a button, and then start a data lab and have your data analysis there. We're also working on adding more applications. So as I said, we have about 50 right now. So we're working closely with our missions to create software packages that are relevant and useful for the communities that they serve. We're also looking for Jupyter notebooks and introductory material so that users, when they come to the platform, they can already have a starting point. They don't see an empty Jupyter notebook. And finally, we're growing our community by having hands-on sessions, workshops where we use data labs in various contexts. And again, it's not just presenting data labs, it's making use of it for various applications, including natural language processing, which we'll have a workshop on in September. One last slide. So if you're interested in a demo of the platform, you can find me at the booth, ESA booth. We have a small booth, but we have lots of goodies. So come next week from Monday to Wednesday. I'll be at the booth, and I'm happy to show you around and, of course, give you a goodie. Thank you very much.
Thank you. So questions?
Thank you, Sander. I really love this project. I was there at JWST, the summer school, when we used it, and I thought it was great. I think, if I remember correctly, the version was 0.30. Is that still the case? And that was about like 6 months ago or so. And I think we struggled with that volume of people. There was about, I don't know, 200 people or so. So how many users do you expect data labs to be able to handle, say, daily users, and how would you sort of improve the system and get to that point? Thank you.
So I think, I don't remember the version. I think now it's 0.13. We keep it at 0. That was the biggest, I think, crowd of people that we had using data labs at the same time. And of course, if you have 200 people at the same time, it can be quite intense. So I think we can cope with those numbers, so hundreds, 200 people consecutively. Of course, we don't expect this many people to run it always at the same time. With 50, 60 people, it works perfectly fine.
Excellent talk. I was actually about to ask the same question. So just how would you handle a large number of users coming on the same time, whether people would, please check back in an hour, you're in the queue, but it sounds like you just kind of get a little bit degraded performance if too many people try to access.
I think the performance was not necessarily degraded by the number of people, but for various, for example, login issues, internet issues. I think it's different if you have the people distributed around the world and they access it through different internets. You have them in the same room, everyone using the same internet, some people using different browsers, etc. So I think if you distribute people around the world, we should be able to cope. So right now, in terms of the hardware and what we can make available, I think we can handle a few hundred people, simultaneously making use of, 64 gigabytes of RAM.
And then if you had a couple hundred people, that would be the point where things would slow down for them?
That would be the point where you're running out of resources, let's say.
Got it. Yeah.
Hi, Sander. Thanks for the great talk. How much data can I retrieve? Is there a limit on the amount? Let's say I want to create a training set based on all the available archival data. Is this possible, or there's a limit on the amount in that sense?
So we have right now, because we want to distribute resources fairly between users, your personal workspace has 100 gigabytes. So that's your personal limit. Of course, we have bigger limits. For example, if you work together with a team, you can request a team workspace together with your collaborators, and you can get a couple of terabytes of data. So you're not really limited by storage, but I think in that case, if you want to download it to your computer, you'll be more limited by your bandwidth.
Okay, it's time. Let's thank the speaker again. So we have finished all the talks of focus meeting. It's really nice meeting, actually. So we hear from very different projects with same sort of common thing, how to provide the data to people, how to manage them, and even including simulation data. So, so we hope we will have a similar meeting in the future at some time after launch. A lot of data from Euclid, SKA, for example, future data. So at last, I would like to thank all the speakers again and all the participants. And then, so I would like to thank Shazlin here. So she prepared everything, including hackathon. So she did a lot of hard work. Okay, thank you.
Thank you so much, Michiko. I should say Michiko is the incoming president of the IAU CB1, so computational, as you want to say?
Yeah. Yeah, so this focus meeting actually planned by, initially planned by IAU Commission B1, computational astrophysics, and you also will be the next committee member. And so, yeah, anyone, if you are a member of IAU, then you can join Commission B1, just write an email, I think. And then, yeah, we will plan more workshop online, so we hope you will join us in the future. Thank you.
So the commission is for you. You are the commission. So join, be active, tell them your needs, tell them what you would like to see, and that way we can grow our computational community and work together to make the strides that we need with this big shift that's going to come. Thank you everybody for coming to the focus meeting. As I said, I apologize. We should have made a week-long symposium, I think, given all of the good submissions that we got. We just were so limited with 2 days. We couldn't showcase everybody's work. So I'm sorry about the posters, but we would really like to somehow include this. And I think the idea is that we will ask in the proceedings if everybody can submit a figure and a small paragraph, and we will try and incorporate this in a big summary of the meeting as part of that, in addition to the invited talks that were included. So I will send more details about that, and then you will all be co-authors of this big paper, and hopefully it will synthesize some of the great results that we weren't able to highlight, as well as the ones that we were able to highlight. Thank you, everybody, and enjoy the rest of the GA. It's time for Africa. Let's go.
So, Shazreen, I don't know if you can hear me. Well, maybe not.